Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside as we jump into Chapter 7 in the Big Ideas Math Integrated Math 1 textbook. Chapters 1 through 6 were on algebra based concepts. Chapters 7 through 12 are not, and Chapter 7 is its own little ditty before we hit 8 through 12. Chapter 7 is on statistics. The actual chapter name, I believe, is... Actually, I forget. Let me look it up. Data analysis and displays. So we get 5 sections of statistic-based things. You might have heard these things before, but they're going to hit different kinds of questions. Let me see how many problems. I'm not prepared. I have everything prepped. I just don't know. 39 questions of things regarding measures of center and variation. The only thing is, I don't know what anything's called. And you might not know what anything's called here either. In the statistics chapter, completely separated from algebra, and chapters 8 through 12, completely separated from the geometry, are going to introduce you to a lot of brand new terms if you ain't seen them before. So the lecture portion is going to help cover that. And then we have questions 5 through 39, well, 1 through 39, but the vocabulary and core concept check, and then questions 5 through 39 to take care of the rest. So jump to the description section down below if you'd like to download this PDF of the actual lecture portion and the problem set and find the timestamps of anything that you're trying to find involved as well. I don't know if we graph. I'm going to guess we don't. I don't actually know. Eventually, I think we do, like bar graph things, histograms, but not in this one. And even if we do, I'm trying to think if we're going to use graph scales. I think we would, but that's not here. You know what you will need is a calculator. Oh, you'll need a calculator for this one. Let me get mine up and running. I'm so not prepped, guys. There it is. Okay. Without further ado, let's go ahead and get started. We're going to begin with the lecture portion. What you will learn. You will learn to compare the mean, median, and mode of a data set. Now, it's likely you've heard those phrases. It's likely you know what those phrases are. But there's more we're going to be able to do outside of this. Find the range and standard deviation of a data set. This is not the same kind of range as we talk about, like domain and range. It has the same idea, but it's not, this is the X, this is the Y, not like that specifically. And identify the effects of transformations on data. I'm curious what they mean by that. I actually don't know yet. I don't get to see this stuff beforehand, really. A lot of different terms. I'll let them expose themselves as they come up. The first one that's coming up right now is measure of center. Measure of center right here. I'm going to read their definition, and I'll interpret it if need be. A measure of center is a measure that represents the center or typical value of a data set. The mean, median, and mode are measures of center. We're going to learn what mean, median, and mode are, I suppose, if you don't actually know. But when we talk measures of center, we're saying where we can find where things are most located for your data set to you. Let me actually just say this on statistics. And this is true of football behind me. This is true of baseball, my favorite sport. There's not one number that represents everything. And I know, especially as coaching softball, a lot of my players focused on batting average this year. I'm like, first of all, for those sabermetrics heads and whatever else, batting average is not what you're going to look for first and foremost. But it's also obviously not the only thing that you look toward. Mean or median or mode aren't looked at alone. You look at everything, and you use them to help emphasize certain parts. Sometimes median's better than mean. Sometimes mean's better than median, things like that. So I just want to make sure that you're well aware of that. Okay, what is the mean? Mean is another word for average. I want to say that because I don't see the word here. Average. Add your numbers up, divide by how many there are. The mean of a numerical data set is the sum of the data divided by the number of data values. Average. The symbol X bar represents the mean. It is read as X bar. Yes, X bar. So when you see this, if there's a data value that is X, we might use the variable X in and of itself. X bar is what we use for the mean of those values. The median. The median of a numerical data set is the middle number when the values are written in numerical order. So if we get a problem set that's not written in order, I'm going to write it in order almost always, even if they don't ask for median. It's just a go-to that you want to do for the problems. When a data set has an even number of values, the median is the mean of the two values, or the average. Imagine if you had 8 numbers. What's the middle number? It's not the fourth number. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 numbers total. Numbers 4 and 5 are the two middle values. So what's the middle number? You got to average those two values. That'll give us the median. The mode. The mode of a data set is the value or values that occur most often. There may be one mode, no mode, or more than one mode. So this is a frequency amount. This is how often numbers appear, which one appears the most. I tend to not use mode as often for different reasons, but it depends on what kinds of ranges of things you're looking at. We'll see how they end up using them. Comparing measures of center. Here's an example. An amusement park hires students for the summer. The students' hourly wages are shown in the table. This is how much they get paid. Why is this one significantly more than the others? Anyway, hope that's not a typo. Find the mean, median, and mode of the hourly wages. Which measure of center best represents the data? Explain. So, taking the mean is calculating the average of these values. Now, they did not rewrite them in order. They just kept them in the order they're in. I'm likely going to, I don't know if I rewrite them in order first before I do the mean. I haven't done these in so long. I got to think about it. But when you do the median, you got to rewrite them in order to take a look. So for the mean, add up your numbers and divide by how many there are. There are 8 total values. You divide it by 8. The mean value is 9.65. Most people see the average as their favorite thing to go to, and I can see why you'll see that. $9.65 is the average. Now, we'll see if you agree on whether the average is the best representation of these values in a moment. The median is going to be half, not half. The average, I was going to say half the distance, but the average of your two numbers in the middle, because if there are 8 values, like I said, numbers 4 and 5 are the two middle values. So add them up and divide by 2, you're taking their mean, and you get the median value of basically $8.70. And then the mode is the number that occurs most frequently. $8.25 occurs twice. It's right here and right here. Everything else occurs once. Therefore, $8.25 is the mode. Now, they did say which measure of center best represents the data. Honestly, I would go with the median. Let's see what they say. They do say the median. Let me show you here. The median best represents the data. The mode is less than most of the data, and the mean is greater than most of the data. And that's what I'd go with. The median seems to really work out that middle. Median can kind of mean middle, and you might say, when is it not best? We can talk about it. But the median really seems to kind of represent, I see a lot of $8 values, middle of the road $8. Yes, I got a $9 one. I got the $16 one, and I get it. Here's the thing about the $16 one. It constitutes as an outlier. Is that one of our words? Maybe that's why there it is. That's probably why they're talking about it. We'll talk about outliers more, but this is one that stands above the rest, and it's just different. It's almost an anomaly. Like, sometimes you want to throw it out because it doesn't represent every other data value, and everything else is in the $8, $9 range, mostly 8. And this represents the median well, whereas this average is above all the other numbers, but that one big one that just stands out in its own way. That's why I don't really like the mean. This doesn't really represent the center, right? These are measures of center. This doesn't really go toward the center of where your values are, and the mode is on the very low end. That's the lowest amount of that's the lowest value, and even though it occurs most frequently, it doesn't really represent what all the other numbers are. That's what measures of center are. In this case, the median best represents it. That doesn't mean the other numbers don't apply. Looking at it all as one is great. So I just want to make sure that makes sense. Oh, study tip. Mode is the only measure of center that can represent a non-numerical data set. Meaning if they said, like, hey, here are all the birth months of people, January, February, etc., for people at a school or something like that, you couldn't find the mean or median. I guess you could find a median sort of by ranking them, but you can't calculate the other ones, right? Mode is a quantity, how many of each. So if the most people are born in August or something, for example, right? That's how that would work. Okay. An outlier is a data value that is much greater than or much less than the other values in a data set. So in the first, actually they say it right here. In the previous example, there was an outlier. It says identify the outlier. How does the outlier affect the mean, median, and mode? Describe one possible explanation for the outlier. So when they say how does it affect it, you have to see what it's like if it wasn't there. What if you threw it out? Now the 1651 is the outlier. There can be a subjective version of deciding what makes something an outlier. There might even be a mathematical version. If it's more than 2.5 times anything else, the next greatest value, if they had something like that, we could come up with it. But this clearly stands different from the rest. Look at your numbers again on this set. These are $8 and $9 values. Then suddenly you have something that's effectively double. Well, it's double the lowest value. That stands way out and way different. When I saw it, this is my first time seeing it, and I looked at this and I said, why is this here? That's clearly an outlier. It's way different than everything else. If everyone else said, hey guys, tell me your hourly wages, $8 this, $8 this, $9 this, $16.50, bazooka, right? That is totally different from the rest of them. Anyway, much greater than the other wages, it is the outlier. Find the mean, median, and mode without the outlier. So take out the outlier. Notice there are only 7 terms now. And I like that they do these examples because now we get to see the mean in a different light. We divide by 7 terms rather than 8. The median now has a middle value. It is the 4th value. Yes, the middle value from 1 to 7 is indeed 4. And it's $8.65, a single number. And the mode still happens to be $8.25. Now, when they say when you remove the outlier, the mean decreases by 98 cents, basically a full dollar to $8.67. Now that mean is pretty good when it comes to a number, but then again, so is the median, which was $8.65. Those are pretty much the same value, virtually the same value. The median barely changed to 5 cents less, and that makes sense. They only added another value. It doesn't matter how big or small it was just another value on that end that wasn't the middle value. So, okay, it makes sense that it can be very little. The mode didn't change. The mode is the same because the most frequent value still is the $8.25 value. Now, if we had multiple people that had $16.50 values, they're no longer outliers. They're just a part of the data set. There's a big jump, and it's extreme, but it's just how the data works. If there's one of them, feels like a pretty good outlier there. Describe one possible explanation for the outlier. Let's read what they say, because this is one that's obviously very open-ended. What can explain why a student would be paid $16.50, whereas the other ones would basically be paid half that amount? The outlier could be a student who is hired to maintain the park's website, while the other students could be game attendants. Yeah, it could be a different kind of job. You're hired with all the others as a student, but you have a different responsibility, and sometimes different responsibilities require different amounts of pay. Not require, but they kind of constitute different amounts of pay. And that's that thing. I don't know what I would come up with, so I wanted to read what they say. And we're going to have to come up with our own, I'm sure. All right, here's another example. I'm going to skip on forward past. You can check it out if you like to. We're going to find the range and standard deviation. Now, these are considered measures of variation. You have to remember that we just talked about measures of center, just how things kind of measure the center, how things describe where you kind of center your values toward, where we're looking for the middle for like this number represents kind of the sum of where things go. A measure of variation is a measure that describes the spread or distribution of a data set. The mean, median, and mode, let's say this right now, did not tell you how spread apart these numbers are. You could have 2 completely different data sets and have a mean of $8.70. 2 wildly different data sets. Ones that are all very closely together in the $8 values, ones that are way different. It's like test scores, right? Someone could have all test scores of 70, their average is 70. And someone have 50, 60, 80, and 90, and their average is also 70. So measure of variation shows how much your data spreads apart from each other. So we have 2 numbers to talk about with that. The range and later standard deviation. One measures the range. The range of a data set is the difference of the greatest value and the least value. In the example of the 70s, all those 70s for test scores, their range is 0. Their highest and lowest score are the same, so 70 minus 70 is 0. From the 50 to 90 one, that range is 40. 90 minus 50 is 40. That's the range from their lowest score to highest score. Let's do their example. 2 reality cooking shows select 12 contestants each. The ages of the contestants are shown in the tables. Find the range of the ages for each show and compare your results. This is another one where writing them in order is really good to do. That's why I said it's really nice to write them in order anyway, despite the median. And show A, you rewrite them in order. 19 is the smallest age, the lowest, youngest age, and 31 is the oldest age. Their range is 12 years. From the smallest, I keep saying the smallest, from the youngest to the oldest age, they're 12 years apart. The youngest on show B is also 19, but the oldest is 48. Almost an outlier, if you will. There's a kind of a bigger jump to 32. Actually, I would call it an outlier. So this range is 29 years. If you remove the outlier, the range is, 13 years, right? Like, hey, what's this 48-year-old doing here? I'm not being ageist, by the way. I'm not that young. So 48 years. So 48 minus 19 is 29 years. Significantly larger range on show B. It didn't mention anything on mean, median, and mode when it comes to average and stuff like that. That's just the range of these 2. The ages for show B are more spread out. A disadvantage of using the range to describe the spread of dataset values is it only uses 2 data values. Very true. That 48-year-old could have been a 60-year-old, whatever, but it's just one number, whereas the others are showing everything different. A measure of variation that uses all the values of a dataset is the standard deviation. Okay, we'll see how deep they get into standard deviation for you IM1 folk, but standard deviation is a massive thing you could talk about in statistics and do a lot with. So I'm sure they're going to go very shallow level. In fact, I'm surprised that they do more than just what the calculator would show, because there's a way in calculator to do standard deviation, and at some point you might do it here, but they're showing you a formula, which is good. Kind of shows where it comes from. I know it's confusing looking. The standard deviation of a numerical data set is a measure of how much a typical value in the data set differs from the mean. And there's a lot more I could say on that. I'm going to try and refrain and reserve myself from that. The symbol sigma, that's the lowercase sigma, Greek letter, represents the standard deviation. It is read as sigma. It's given by, the standard deviation is, and it's the square root of this massive thing. Now, this looks a little confusing. This x sub 1 and x sub 2, all that, these are all your data values. So x sub 1 could be the smallest one, whatever. It's just one of them. X sub 2 is another one. X sub n, it depends on how many data values there are. There are n values in your data set. So this could be x sub 8 if there are 8 of them, etc. So you're just choosing all those things and you're subtracting something. What are you subtracting? X bar, the mean of the values. So you got to find the difference between how far apart a data point is from your mean. You're going to subtract them. You're going to square that individual quantity. This is almost like the distance formula. You're going to square that individual quantity, and then you're going to add the next set over. That thing squared, plus that thing squared, etc. You divide by the number of terms that there are, and then you take the square root of that value, that whole thing. It's a lot to do. I don't know if they're going to talk about disadvantages. I'm trying to look for it. One disadvantage of these is it takes a long time to do compared to range. So range is a nice quickie. This one takes a lot longer. So you're doing all those things. It looks like they're doing all that stuff here. They mentioned this word variance. Variance is the thing before you take the square root of everything. So sigma squared. I forget what variance represents. I know that the word is variance. I forget what it represents when you look at the number and what it means. I know what standard deviation means in full. And I feel like I'm not going to over-describe it. I might state some parts about it, because you might still look at that and say, what are they talking about? I'll try and give one version of it in a little bit. A small standard deviation means the data are clustered around the mean. A large standard deviation means the data are more spread out. And yeah, that's basically all it means. When you get a standard deviation of 2, that means plus or minus 2 from the mean is about how far most of the data are. Plus or minus 2 test points, plus or minus 2 years and age, whatever it is that you're talking about, and we're going to do that on ages right now. The bigger the standard deviation is, the more spread out things are from the mean. So you can collect the mean of your values and the standard deviation, and you're actually learning a lot about your information, where they're centered and how much they vary. Find the standard deviation of the ages for show A in example 3 and use a table to organize your work. All right, I mean, I'll do what I do. I feel like a table is a very nice way to be able to do that in organizing it. So they calculate the mean as a whole right here. They add all the ages and divide by 12. They get a nice clean 25 value. You find the distance. What is this called? Is it called the residual? I think these might also be called residuals. But find the distance between your value and the mean, how far away they are from each other. -5 means that this person's age is 5 years younger than the average, right? And a 4 means they're 4 years older than the average, etc. But you subtract them and then you square your values. I might even want to copy this table down and paste it later based on the thing. So if we use a table, which we likely will, guys, keep in mind, this might be a long video. This is one problem on standard deviation, and this is all the stuff you have to do on it. It's going to be a lot, and then you have to use the calculator. So these numbers are squared. You're going to add those values up. I don't know where they do all this. Okay, these all add to 212. You divide by how many people there are, how many contestants. There are 12 of them. And you take the square root of that number. Now they're rounding to the nearest 10th. I'll make sure to do the same thing. And you get about 4.2. Now this is the standard deviation of here. They say this. This means the typical age of a contestant on show A differs from the mean by about 4.2 years. I don't want to speak too much on it because they're probably not going to have us do it. But this means if you add 4.2 years or subtract 4.2 years, let's just say 4 to just be even a little more rounded. If you add or subtract 4 years from the mean, if the mean is 25 years, you add and subtract 4 years, it means the majority of your contestants are between ages 21 and 29. Because that's adding and subtracting 4 from there. Now, what's the majority? It's not much. They actually say that's 68% of them. If you add and subtract another 4 years from there, that covers about 95% of them. Now, I'm not going to say much more beyond that. But from ages 17 to, which there's no one age 17, from ages 17 to 33 then. Standard deviation and mean are two very good ones to use when you have most of your stuff centered very symmetrically. When you have something asymmetric, it's better to use mean and things regarding range. Okay. I'm going to keep moving on. Effects of data transformations. Yeah, I'm curious here. A data transformation is a procedure that uses a mathematical operation to change a data set into a different data set. When a real number... Oh, I see what they're meaning. Okay. So when you change everything about it. When a real number k is added to each value in a numerical data set, the measures of center all should change, and they should all change by amounts of k. By adding k to the original measures of center, your mean is going to be k. Now, k can just be a number. If k is 3, your mean becomes 3 bigger, your median becomes 3 bigger, and your mode becomes 3 bigger. Everything shifts up by 3 if all your data values become 3 bigger. Measures of variation are the same. Now, that makes a lot of sense. Your range, we had ages, 19 to, let's say, 48, I think it was, on show B. If you add 3 years to those, if they all get 3 years older, that range is still the same, and the standard deviation is still the same. But the average, the mean is not, the median is not, the mode is not, right? Those are different. That's using addition or subtraction. By using multiplication. Now, I don't see a time that I'd ever multiply by a negative number, so they're just kind of giving that stipulation. When each value is multiplied by some real number k, where everything is doubled, for example, the measures of center and variation are all also doubled. You will all multiply that by that thing. That's kind of how that would work. If you double every value, then the mean is doubled, the median is doubled, the mode is doubled. The range is doubled, and the standard deviation is doubled. Everything is doubled in that sense. This is not all about doubling. I'm just using a number example. Consider the data in example 1. This was the hourly wages. Well, they changed. Looks like they're 50 cents bigger, which is what they're going to do here. Find the mean, median, mode, range, and standard deviation when each hourly wage increases by 50 cents. Find them when each hourly wage increases by 10%. So there's a part A and part B. I have hiccups. I want to address these really fast. Okay. What was I saying here? Oh, so we saw the parts A and B. So it's two different questions within. Okay. So part A, let's increase everything by 50 cents. Now they're showing two different methods. One, and I'll probably try one versus another on different problems, right? Method number 1, make a new table by adding 50 cents to each hourly wage. So this is more discovery of it and less knowledge of what's actually going to happen, where you're actually making everything 50 cents bigger. Then calculate those mean, medians, and modes. I don't know if you remember what the old numbers were. I don't specifically. Well, I will based off what these things are. But now the new mean is $10.15. Remember, it was in the $9 amounts. The new median is $9.20 instead of, I think, what was $8.70. And the mode is $8.75. Remember, that was $8.25 because, well, these got 50 cents larger, and that one's just as frequent. It's more frequent than the rest, so it makes sense that's 50 cents bigger. The range of standard deviation we didn't do the first time, but you can bet that that's what they were. Because method number 2 is do this. Find the mean, median, mode, range, and standard deviation of the original data set. Now, we did. Okay, so here were the originals. What you'll notice is the mean, median, mode are 50 cents larger than they were, whereas the range and standard deviation did not change. Despite the fact that everything added this much more, it's still that same highest and lowest difference. And standard deviation, how much 68% is from the mean and things like that, that's still the same value, just because you added a set from there. I prefer doing this because to me it's less work. I don't have to rewrite each number of adding new values, and we know what it goes with. I'm probably going to do more method number 2 when I can. but they're showing you that that's where they change versus not change. What's this one here? Oh, after that, oh, I'm sorry, I didn't finish. After, because we're not just comparing these two, when you take this mean, median, and mode, then you add 50 cents to these three, and then you don't add 50 cents to these two, right? I was comparing them to what we had on top. Okay, we understand it. Now, B is increasing by 10%. That's a multiplier. You actually multiply by 1.1. I'm trying to think if we did that stuff before. I think we did. Exponential growth, right? We multiply by 1.1. When everything multiplies by 1.1, you don't just multiply these numbers and recalculate. I wouldn't recommend that method. Once you recognize what it is that we do, you multiply all of these values here by 1.1. And then I guess you round it. So these ones here, 10% changes everything by 10%. That includes the range. That includes the standard deviation. This must be about the word problem. I'm going to leave it. This looks like an outlier, though. That's all I'm going to say. Okay. Okay, that's the end of the lecture portion. Let's start with let's go to the vocabulary and core concept check, answer those questions, and then we have questions 5 through 39 to take care of. This might be an ambitiously longer video. In a data set, what does a measure of center represent? What does measure of variation describe? The measure of center, literally, it represents a center value. So it represents a center value, a center or a value or a typical value that you can refer to say where your things kind of surround. And you have to kind of determine, there are 3 different measures we talked about, mean, median, and mode. There's no one that's better than the other. It's problem dependent, I should say. There are some that we focus on more. It depends on the situation. The measure of variation, without me trying to say variation or range, the measure, measures of center, a measure of center represents a center value or a typical value. A measure of variation, I think they used another word as well, represents the, I don't want to say range or variation, the distribution of the data. They might have used that word, the distribution of the data. Oh, it's hard for me to come up with the answers. Describe how removing an outlier from a data set affects the mean of the data set. Well, if it's a larger outlier, that value is going to get smaller when you remove it. And if it's a smaller outlier, that means going to get higher because your mean pulls toward the outlier. Now, the median doesn't pull significantly as much in comparison, right? It just kind of jumps as far as you go from 7 terms to 8, from 7 data points to 8 data points, things like that. It jumps depending on what the next value is, but it doesn't jump in that substantial way based on how the mean does that. I will say this, when you remove it, that mean shrinks a lot more toward a center like the median would be, so the mean gets closer to the median when that happens. So when you remove an outlier, when removing an outlier, because your mean shrinks that way, the mean gets closer to the median. Gets closer to the median. Okay. So I'm going to say that in a general sense. Create a data set. This is open-ended. Create a data set that has more than one mode. Yeah, so the only mode that we've seen so far for something, or that they've asked about, has been one where that literally had 2 instances of it and the rest had 1. So what's something that has more than one mode? I'm going to write this just random order. There's no context to this stuff. 4, 3, 1, 4, 6, 1, 2, 5, 1, 4, 7. The mode in this case, or the modes, are ones that appear equally most frequently. There are 3 4s that appear here. If I did this right, there are 3 4s. Modes 4, and there are 3 1s that appear. Nothing else appears equally as many times. If a 4 appeared 4 times, 4 would become the mode, despite the fact that 1 is second to it. So there's more than one mode in this data set here. And then number 4, what is an advantage of using the range to describe a data set? Why do you think the standard deviation is considered a more reliable measure of variation than the range? An advantage of using range, I don't know if they mean in comparison to measures of center, or if they just mean for measures of variation in comparison to standard deviation. I'm going to guess they're saying in comparison to standard deviation because we haven't been able to talk about it yet. Range is easier to calculate, significantly easier to calculate than standard deviation. Let me give myself more room on the bottom here. Now, why is standard deviation perhaps more reliable? And I'd agree it is. You have to know how those numbers actually work, though. But how would you consider it more reliable? You use more data. You use more values. Standard deviation is a more reliable measure because all the data points are used. As opposed to just the maximum and minimum. Now, the maximum and minimum, they didn't actually say those words before. Those are actually words that, those are actually words that they would use in statistics for the highest and lowest values. And I imagine, I feel like I have to sneeze, I imagine that they will be using those in a future section. I actually don't know what the sections are that we're covering as a whole. Sorry about that. When we get to them later, we'll actually know what they are. Okay, guys, we're going to jump into the numbers 5 through 39. I imagine this might take a while. There are a lot of calculations to do. Now, I've slowed down so far. We spent over a half hour on the lecture portion. I really feel like, honestly, right now, and I don't know how many people watch the lecture portion as a whole. Kudos to you for watching. I hope you absorbed it because I really slowed it down. I feel like my slowing down really reminds me of what I did in section 1.1 of this stuff. Because guess what? This stuff is brand new. It's almost literally like a new class right now. There's no solving for X kind of stuff that we're doing here. There's no graphs and things like that. Everything here is brand new, and I really wanted to slow that stuff down for the people who are learning it for the first time. So I hope that was with a lot of intent. I hope that was helpful for you. Now let's jump into this portion, and I'm going to start the timestamp for problem number 5 right here. If you're jumping into this portion right now and watching, we're going to start problems 5 through 39. I did a whole half-hour lecture portion, so I might go significantly faster on these parts. Not that it'll go fast, a lot of calculations, but you're going to have to watch the lecture portions to see how those things go. That's why I do the lecture portion for you guys. So check that out if you need to. Okay, we're going to go ahead and go to everything else here. In exercises 5 through 8, we are going to find part A, find the mean, median, and mode of the data set. Part B, determine which measure of center best represents the data and explain. Some of it can be subjective, but I hope that they give you problems that it stands out, that we can look at them for ourselves, especially if it's your first time trying these things. So, number 5, we have the data points 3, 5, 1, 5, 1, 1, 2, 3, and 15, which stands out above the rest, right? Now, I still don't know whether I'd like to write them in order first or not. I feel like I want to. That is important for median and for other things that you do. So I'm going to rewrite these in order. I'm going to find all my ones. There are 3 ones here, which can help for mode later. There's a 2. Let's cross them out as we go. 1, 1, 1, and 2. There are 2 3s, 2 5s, and a 15. 2 3s, 2 5s, and a 15. It might be best that you actually just count it out, make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. All data points are covered. Now, I rewrote them in order. Now, part A is calculating the mean. The mean means the average, and they actually use the variable x bar to represent that for mean. So we're going to add these values together and divide by how many values there are. That's how we calculate the average of something. And this is context free. I don't know what this is actually representing as a whole, but it's going to be this. This is, again, for the mean. 1 plus 1 plus 1 is 3, 5, 8, 11, 16, 21, 36, and 36 divided by 9. So I can do that one without a calculator. That average is 4. The average for these is 4, the mean. The median. The median takes your list. This is where I'd likely write it in order from here, but the median, there are 9 terms. The middle value is actually the 5th value, which is this one right here. It is the middle number because there are 4 on the left and 4 on the right of that number. So the median value is 3. And the mode is the value that occurs most frequently. Not second most, which one is most frequent. If there's a tie, you list them both. But there are 3 ones, so 1 being the mode is what we're going to put there. I don't know why I circled that one versus boxing the others. Let's change that. So, which one is best represented? I would say the median. It's not just in the middle, whatever. It kind of really seems to lean toward that center. 4 isn't even represented in the values, but it's more than the majority of your values, and the mode is less than the majority of your values. The median really tends to work toward that middle in this case. The median, oh my goodness, let's fix that size. What do they say? Which best represents the data? The median best represents the data, in my opinion. Now, the way that they said it in the example stuff was they kind of explained why the other ones weren't. And we could say the mean is greater than most of the data, and the mode is less than most of the data. Now, if I have to do that each time, I don't know. If I have to do that every single time, I'm going to try and do the best that I can. Now, what made the mean go up so much? Not so much, but to 4 in and of itself. It's that outlier, man. That 15. 15 really made things pull itself over. If not, I like to use the average if there aren't outliers. I like to go toward mean if I can. Now, mode might really tell all on something. It's not, whoops, number 6. It's not always the case that that's going to happen. I'm curious as to find a mode that would make most sense of our stuff. We'll see. Number 6. And I'm going to not write these in order until we hit the median, okay? So we got 12, 9, 17, 15, and 10. This was part B over here. All right, part A, the mean. X bar, we have to add these. There are 5 terms, so we are going to divide by 5. That's 21, 38, 53, 63. And 63 over 5 is 12.6. 12.6, that is your mean. The median, I'm just going to stick right here. Let's write them in order. There are 5 terms. The smallest number is 9. Then 10, 12, 15, and 17. The middle number here is 12. The mode is the one that occurs most frequently. If it is a tie, then among all terms, then there is no mode. The mode would be none. So when it comes to asking which one measures the center of data most, do not say mode. I'm actually going to go toward mean this time. Listen, median's not bad as 12 or whatever, but because there aren't really any outliers here, it's just a natural spread. You kind of just hit everything. 9, 10, 12, 15, 17. 17 ain't an outlier. 15's pretty close to it. It's just 3 away from 12, which is just 3 away from the lowest value. I would say that the mean works best. Given that there are no outliers, that's where I'd lean toward mean. So the mean, I'll just put mean. So part B, mean, there are no outliers. That's a good reason to talk about that one. Obviously, mode can't be it in this case. Median's good, and it's really close to mean. I like using averages when I can, though. All right, number 7. Number 7, we have 13, 30, 16, 19, 20, 22, 25, and 31. I almost feel like I can type all these things out, except for when I calculate the mean, which is the beginning of this. So part A, the mean, X bar. Let's add them up. This time I'm not going to write out adding them up. We know what we're supposed to do. Let's just count how many terms. There are 8 of them. So 13, 43, 59, 78. Is that right? 78, 98, 120, 145, 176. 176 divided by 8. That does divide by 8. That's 22. So your mean here is 22. Median, again, you have to write them in order. And writing them in order is good because then we can identify outliers as well if we have them. 13, 16, and 19. 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and 31. Is that all of them? 1, 2, 3, 4, 5, 6, 7, 8. Yes. So the median, there are 2 middle numbers, 20 and 22. We actually have to add these 2 up and divide by 2. We are taking the mean of the 2 middle values. That's 42 over 2, which is 21. Now, 21 is also half the distance between 20 and 22. When you average 2 values, you calculate their midpoint. I'm sure we're going to talk about midpoint stuff more in geometry, and I'm going to mention that exact same thing. So what's halfway between those numbers? Clearly 21. and that is the median value. Very close to 22, by the way. Mode, also no repeats, right? Once again, there is no mode. Whoops. Not none, but none. Which one's better to use, 22 or 21? It's argumentative at that point because they're, again, virtually the same thing. But for part B, once again, I don't see an outlier. This thing just has a typical spread of stuff. Oh, not right here. It has a typical spread of stuff. That's a 30, by the way. There ain't no outliers as far as I can tell. Mean is pretty good. It's subjective, I suppose, but if you ask the book, I'd say the mean, there are no outliers. Once there are outliers, I tend to trend toward median. I want to find out in what instance I'd really talk about mode, because there could be examples. There very much could be. Maybe it's this one. I have no idea. Let's see. Number 8. Let's try and type this one out and see how it goes. I'm just going to write the 8 by hand first. Let's see how much we can do here. So number 8, I got... Let's see if it's faster for me even. 14. Where's a comma? Oh, boy. 14, 15, 3, 15. Did I write it all correctly? I hope I did, because I like to copy down my problems. All right, so part A, the mean. Now, I can't put an X bar there. I'm going to put X right now. I'll put the X bar afterward. So, 14, 29, 32, 47, 61, 75, 93, 108, 116, 132. So 132 divided by, was that 10 numbers? 10. That'll be 13.2. So there's our mean. The median, we have to write these in order. ChatGPT, please rearrange these numbers in ascending order. Median. Smallest number is 3. It seems outlier-esque. It really does. I know there's an 8 there. This is where I'm really looking to the mode more, I think. Let's see. 3, 8. Is the next number 14? 14. How many 14s are there? 1, 2, 3. There are 3 15s, and there's a 16. Is that 1, 2, 3, 4, 5, 6, 7, 8, 9? We're missing a number. 3, 8. Oh, 18. That 3's not really an outlier once the 8's there, but it also kind of is. That 8 outlies itself, but look, imagine if the 8 wasn't there. Now 3's an outlier. These numbers are blah, blah, blah. That 8 really says, well, I can there stands to reason why 3 exists now in a non-anomalistic way. Now, that's not the median, by the way. That's just the sorting of the values in alphabetical order. In ascending order, there are 10 values, so these are the 2 middle values. So what is the median? It's halfway between 14 and 15, which is 14 and a half. That is your median value. The mode, this is almost what I thought we were at. The mode is which number occurs most frequently. 14 occurs 3 times and 15 occurs 3 times. There are modes. The modes are 14 and 15. Now, for number 8, and for number 8, which measure of center best represents the data? Explain. Mode isn't bad. Median is right in between those modes, so median actually works almost a little better with that. Mode's not bad, but there are 2 of them. So it shows there. I want to point to say mode, but since median is right smack dab in between the modes, for measures of center, I don't want to vary myself away. So just because it's 14.5, I'll go ahead and say median again. So median, it's in between the modes. It is between the modes. Yeah, that mean got pulled down because that 3, whether or not you call it an outlier, that thing was pulling it down quite a bit. Mode ain't bad as an answer, though, but there is more than one, so it's not one center. Maybe that's why we wouldn't say mode. Number 9, analyzing data. The table shows the lengths of 9 movies. Find the mean, median, and mode of the lengths. Which measure of center best represents the data? Explain. So the same kinds of questions. One difference is we might use context. This is how many hours they are. So our answers will be in hours. Now, they also represent the table this way. So even though we have this table, I'm right now going to write them in order. So the shortest movie, pretty short, 1 1/3 hours. That's 1 hour, 20 minutes. There are 3 of them that are 1 2/3 hours. That's an hour 40 each. 1 2/3, 1 2/3, 1 2/3. There are 3 of them that are 2 hours. Oh, I didn't see the 3-hour one. There are 3 of them that are 2 hours long. There's the 2 1/3, 2 hours, 20 minutes. And then there's Oppenheimer at 3 hours. So 1, 2, 3, 4, 5. Oh, 9 of them, a 3 by 3 there. So find the mean of these things here. Did I ever do X bar up here? I did not. I apologize. The mean. We're going to add these here. So it's kind of bizarre to do. I don't like dealing with mixed numbers, but here they are. I'm going to do as best I can just based off this. Just these two add to 3 hours. This one and this one add to 4 hours. And then that's, wait, so 3 plus 4 is 7. Excuse me. 10, 12, 14, 16, 17 and 2/3. So 17 and 2/3 divided by 9. Again, before I jump to the calculator, let's be reasonable. Let's look at this in a different way. 17 and 2/3 is also 53/3. When you divide by 9, you're multiplying by 1/9. That makes this become 53 over 27. That looks really weird. So as a mixed number, that's 1 and 26 over 27. Just a tick under 2 hours in terms of that. If we went toward decimal, let's do that. What's 26 over 27? 26 divided by 27. That's 1.96 hours about. I want to go in terms of minutes. I'm going to multiply this by 60. Sorry, you can't see my calculator. It's about 1 hour, 58 minutes. 1 hour, 58 minutes. That is the average of these. Okay, no matter which one you put there, this is the only one that's exact. That's the only one that's based off the fractions. That's why I feel like that answer would apply almost most. Median. I did write these in order. So the 5th movie in this 9-movie set is going to be the median. The median in this case is 2. Median is 2. 2 hours. I'll have you guys know, I tend to use median, even if you're not convinced on median, I tend to use median most often when describing test scores. Not average test scores. The test scores for my classes, the median score is this. Because you're going to get students who get like a 0, like, you know, someone who didn't study, someone who doesn't bother, they don't try, they're lazy, whatever. I don't want that to pull down my average in a way that doesn't really qualify to those who applied, but they're still a part of the set. So median is still there. You know what I mean? So that's, whenever I talk about, I don't like to talk about average test scores and things like that. I do the median. Not to make myself look better or anything like that. It's just, it represents the data better. That would be, hopefully that makes sense to you and why you would do something like that. Why outliers kind of really sway things. If I remove outliers, it's a different story. The mode, 1 2/3, let me delete these circles. 1 2/3 is used 3 times and 2 is used 3 times. That's the modes. So the modes in number 9, there's 1 2/3 hours and 2 hours respectively. Those are the times that occur most. Now, movie run times aren't exactly these things each time. Oppenheimer is exactly 3 hours, though. That's why I brought that one up. But those are the mode times. Which measure of center best represents the data for number 9? Mean and median are virtually the same once again, but they are asking for one versus the other. What's 1.96 versus 2? This seems to have a pretty even spread of the data, though. So I kind of like the median for that involved. I know there's not really an outlier per se. I like to do median more than you'd think, especially when it's a little easier to calculate or figure out. But I like the median there. Mean ain't bad and mean's pretty much the same anyway. But median, there's a pretty even distribution of everything. The data is evenly distributed for that. Again, if you say mean, I'm not going to say you're wrong. What movies these days are an hour 20? What? Toy Story 1? I mean, but that's not these days. That was made in like 96, yo. Like 30 years ago. 28 years ago from this recording. Number 10, analyzing data. More of the same kinds of questions. It's just a different question, different context. But they're tailoring to me. I like movies. I like stocks. The table shows the daily changes in the value of a single stock over 12 days. Maybe this is day 1, day 2, day 3, etc. So they're not in order. And they can gain value. And if they're negative, they can lose value. Part A, find the mean, median, and mode of the changes in stock value. Let me copy down the data first. Let's find the smallest number. Now, the smallest is the one that's the most negative, the largest negative. So, one day, it lost $13.78. That was the most. And then $3.01, $2.41 lost, 28 cents lost. It's all uphill from here, baby. We're now going, there's 66 cents and 67 cents. I'm looking at the $0 amounts. So 0.66 and 0.67. I'm actually going to run out of room on this single list right here. Is that 6 numbers? There are 12 numbers total. So those are my first 6. Then we're going to $1 values. I got 105 and 139. These are dollar amounts, by the way. I know I'm not writing the dollar symbols here. Sorry about that. $2 values. There's a 203. I should really cross these out as I go. 203, 220, 264. That's 5 of them. There must be one more. 402. Is that the last one? So even though there are more positive amounts, they don't go quite as extreme as that lower amount. I'm curious to see if the mean is actually even a net positive or negative. I don't know if this is a net positive or net negative. So part A on the mean. I am going to use the calculator here. I'm going to add these up and divide by 12. So I'm going to jump to the calculator for you with you. So we got negative 13.78 plus, minus actually, because we're subtracting something. So minus 3.01 minus 4.1. Plus, all right, now the positive is 0.66, 0.67. All right, I'm going to press enter here. This is not the mean. This is just the total. So the total, it's net negative. So it's actually lost more than it's gained over the course of those 12 days. So the mean here is you divide negative $4.82 by the 12 days that there are. So I'm going to put divided by 12 there. And I'm getting, I have to round this thing. It looks like this. It's basically negative 40 cents on average. So about 40 cents lost. And I want to use the units there as well. So around negative 40 cents. I always forget on these dollar things, should I put the dollar sign and then the negative, or the negative and then the dollars? I don't even know which one looks good. I don't like looking at negative money. I feel like the negative should go first. Does that look right? I don't know. I'm going to put that. But that is our mean. Okay. Median. I have them in order here, and there are 12 values. These are the two middle values, 0.67 and 1.05. That's the 6th and 7th value. We got to take their mean and divide them by 2, right? Find the midpoint of those. Again, I can do that. 172 divided by 2 is 86 cents. So there's an 86 cent median, 0.86. And that's positive, by the way. Now, to you, the mean is more important. Like for you as a whole, you're like, but Mr. Robinson, I have a positive median and a negative mean. I've lost money over those 12 days, and I get it. The median's still more representative of how much that $13.78 outlier really threw things off for your average, and how much it's maybe an anomaly and doesn't still represent the center of your data. Doesn't matter if it's net positive or net negative. The center of your data is thrown with the mean by this value to me. That's why I don't think mean's going to be my best representation of this. Mode, there isn't one. I don't remember a repeat of values, and I don't see one there. So there is no mode. There is none mode. So part B, which measure best represents the data? I'm going to say the median. Now, I'm not going to get too deep in the written explanation. I hope that's okay. Just the median. That mean, there is no mode, and the mean was constructed given this to be an outlier. This was a day where things happened. I'm not saying you can erase the day, but had the day not occurred, had you not looked into that day and things, and again, that's hard to say given that, but it is an outlier, your mean would be net positive. Your average in there. And I know you're dealing with a loss so far, but that's not representative of your data as a center. And I want to make sure that that makes sense. That's why I keep emphasizing that one over and over. Part C says, on the 13th day, the value of the stock increases by $4.28. How does this additional value affect the mean, median, and mode? Explain. It says the value of the stock increases by $4.28. Wait, I missed the thing. How does this, so we have to use that number there. I got to figure out whether that's the stock value or the change in stock value. It says increase by 428. So, okay, yeah, I think we just add a 428 to our data set. So on part C, and it's good, by the way, it's very good that in my calculator, I used, hold on, I'll just put include 428. It's very good that I use this sum value right here, and I have that negative 4.82, because guess what? Now I just have to add a 428 to that. So for the mean, this previous work here, I just got to add 4.28. Well, I guess I could do that as well. And here you get negative 54 cents. We're still in the red, but we're getting there. So the mean is now 54 cents divided by, now there are 13 values. So I divide that by 13, or 13 days, I should say. It's around negative 4 cents on average. Per day. On a per day average, it's around negative 4 cents. The median, now your middle number is the 7th value. If I include 4.28, that would be written in ascending order right here. So it's the highest value. It's your new maximum, if you will. So this shifts now your, it's the 13th term, and that now shifts your median to just be this $1.05 value. That was a pretty drastic shift in comparison. That's 105. And I think they said, they didn't just say calculate them, they said how does this affect them? So I'm going to have to say how much they changed by. I'll just say whether they changed or not. I think there's that. Mode, there's no change in mode here because you know, whatevs, right? So how does the additional value affect mean, median, and mode? The mean increased. You have to keep in mind, we went from a larger negative value to a smaller negative value, so therefore we are gaining money. The median increased by a significant amount, and the mode was no change. Increased, and no change. Like, not change as in cents on the dollar. Haha, change as in no change. All right. No difference. Okay. In exercises 11 to 14, find the value of x. They say for the data points 2, 8, 9, 7, 6, and x, that the mean is 6. X bar equals 6. How do you do this? Well, you don't try numbers until it works. We can do this. This is an algebraic set here. We add all our numbers, including x. We divide by how many values there are, and you get your mean. When we divide all our numbers by 6, we get 6, which is to say all these add to 36, and you'd be right. Algebraically, we would say multiply both sides by 6 to get those out of the way. 2 plus 8 is 10, plus 9 is 19, and 26 and 32. So we have x plus 32, and that equals, well, first of all, divided by 6 equals 6. But when you multiply both sides by 6, like I should have done before, we get x plus 32 equals 36. Subtract 32 from both sides, you get x equals 4. I was going to say 34. X equals 4. That's the value that you need to do there to average as 6. Number 12. Got 12.5. Negative 10, negative 7.5, and x. They state here, once again, the mean is 11.5. No change in what we do. Same thing as before. We add our numbers up. Now, if a number is negative, you subtract it. You're adding the negative. We don't know what x is yet. I'm going to assume it's positive, given that my average is 11.5. I'm assuming this is the biggest number, actually. Divided by 4, we get 11.5. So I'll do two things in one, y'all. I am going to kind of write them in one this time. Multiply both sides by 4. 11.5 times 4, 46. 12.5 minus 10 is 2.5. Minus 7.5 is negative 5. So I have x minus 5 is, did I say 46? 46. Add 5 to both sides, and you get x equals 51. Significantly bigger. An outlier of sorts. When you only have 4 values, I don't know what's truly an outlier, really. But that still kind of is. Now, this is a small sample size, but x is 51. Number 13, they're going to talk about the median this time. Now, they ranked their numbers in order already, and that's nice. They're even probably showing you where x would belong naturally with this set. Because they're saying find x, and it's actually a part of the median. It says the median is 14. For the median to be 14, either your middle number has to be 14, or the average of your two middle numbers is 14. And it's an either or based on how many terms there are. They're an even number of terms, 6. So we actually have to average these two numbers and get 14. So it's really no mathematical change from these problems and numbers 11 and 12. You're still averaging numbers, just not all of them. So add 12 and x divided by 2. If I multiply both sides by 2, in this case, 14 times 2 is 28. 12 plus x is 28. Subtract 12 from both sides, you get x equals 16. If you're quite savvy, you can understand that 14 is the average, the midpoint of your two numbers. 14 being the midpoint of 12 in a number, that other number is 16. 14 is half the distance between 12 and 16. Some of these things you can kind of do here, and you don't literally have to average, but it's good to state that. So maybe we can talk about that one here on number 14. Only 4 numbers. The median is 51. I wish they had one on mode. The mode is 45. What is x? 45. Median equals 51. Now, it is based on 45 and x. If I take the midpoint of 45 and x, I get 51. 51 is 6 away from 45, so x is 6 away from 51. So x should be 57. I'm going to say that right now. But we're still going to do this. 45 plus x over 2 equals 51. Multiply both sides by 2. We're going to get 45 plus x equals 102. Subtract 45 from both sides, you get x equals 57. That's a 7. That's a 7. So x equals 57. There is your median. Excuse me. There is your x that gets you your median. I apologize if I called these medians and means before. They are not those. They're the values that get you your mean and your median. We knew that. Number 15, analyzing data. The table shows the masses of 8 polar bears in kilograms. I don't know how kilograms work. Obviously, polar bears are very heavy, but I don't know how much I weigh, for example, in kilograms. So these numbers freak me out alone just by looking at that. Like, those are big. Even if they were in pounds, that's freaky. And I don't even know if kilograms are more than pounds or not. Identify the outlier. How does the outlier affect the mean, median, and mode? Clearly, 62 is the outlier. So let's copy down the values still. We still need mean, median, and mode in general. So I'm going to write the numbers in order, 62 being first. No 100s. There's a 200. There's 262. The 300s, and this is just me looking at the values. So 351, 358, 364, and a couple in the 400s. 1, 2, 3, 4, 5. 455, 471, and there's a 500s. 471 and 553. 62 stands out. It's more than 200 away from the next smallest number. All these are at least within 100 of each other. So as long as it keeps spreading itself naturally through the set, 553 ain't no outlier here. So for part A, the outlier is indeed 62. How does the outlier affect the mean, median, and mode? That doesn't necessarily mean they want you to calculate it here, guys. They're just asking how it changes the numbers. Does it increase, decrease, things like that? I think we brought that up for a previous question. The outlier would totally decrease the mean. It weighs down your averages when it goes in there, right? 62 is a factor, and it's like having 0. That pulls that down a lot. So the outlier decreases the mean. It also decreases the median. Maybe not as significantly much, but consider what this would have looked like with the outlier. The median is the average of these two values. I'd assume it's 361. Without it, it's just these values, and now it's 364. So without, excuse me, yeah, the outlier decreases the mean. So it goes from, that's that. So the median also decreases. It goes from 364 to 361, but it wasn't substantial. The mean and median. The mode doesn't change because there isn't a mode. The mode doesn't change because there wasn't ever a mode. They never asked us to explain why these things are, but that's the mode's explanation. Part B, describe one possible explanation for the outlier. I'm going to say it's a baby cub, or whatever you call it. It's a baby polar bear. It's a younger one. Not like a starved one or something like that. The 62 kilogram polar bear is an infant. Do they consider young? I'm really bad with word things. Do they say infant animals? It's a young one. It's a baby one. I'll say a baby. Is a baby. It's a little one. Oh, it's so cute. There's a great thing I heard once before. You know, you probably hear these things as well. Like, hey, when a bear comes at you, you know, play dead and stuff like that. But you've also probably heard other things. Oh, you're supposed to charge at it. You know, things like that. I actually heard a rhyming thing, and I'm going to keep it in mind if I ever encounter a polar bear, but you have to note its color for it. So they say, if it's brown, lay down. So that's kind of that. I don't know if it's play dead, but show that you're not a threat to them. I guess on survival instinct alone, it's supposed to be the whole, if it's brown, lay down. Okay, good to know. Now, I have to identify between brown and black when I see it, because I think when they're brown, sometimes they're very dark brown. But like that old grizzly bear thing that's very brownish, I'm going to lay down for it. Now, by the way, don't climb a tree. They can climb trees. Yes, they can climb trees. Okay, if it's brown, lay down. If it's black, attack. Does that mean fight? Like punch it? No, it means you're supposed to and like go, you know, like make yourself appear big. Arms raised and stuff like that, appear big. I don't know if you charge at it, but appear big and come at me, bro, with it. Show your dominance against the black bear. I do that at Black Bear Diner all the time. Like, what would you like, honey? I like a Denver omelet. If it's brown, lay down. If it's black, attack. And the one, it shouldn't make me laugh, but it does. If it's white, good night. You're dead. Polar bears, and I know we don't think of them as very cute, and they're cute. They're very adorable until they're tearing your organs out limb from limb. Sorry about this. Sorry about being very brutal for you guys. Polar bears, first of all, you're probably on their terrain on ice. You can't outrun them or anything like that. But also, man, they are straight up predators. They feign on just getting food. They want food and they want you is kind of the idea behind it. I'm not saying if you see a polar bear, you're dead. I'm saying that if there's an encounter where they're coming at you, again, on their turf, I don't think you got a snowball's chance. No pun intended. I don't think you have a snowball's chance against him is basically the idea. So, I'll remember that rhyme when I encounter the white polar bear, that I gotta let my life flash before my eyes. If it's white, good night. All right. Unless it's a cute baby. If it's a baby, maybe. I just invented that rhyme. All right, number 16, analyzing data. The sizes of emails in kilobytes in your inbox are 2, 3, 5, 2, 1, 46, 3, 7, 2, and 1. Identify the outlier. Is there an outlier? I almost want to do Blue's Clues on this. Do you see the outlier? Dora. Do you see the outlier? I'm not good at that. All right, I'm going to stop. I'm having too much fun. 1, 1, 2, 2, 2. Oh my gosh, I'm writing upwards. 3, 3, 5, 7, 46. Is that all of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I got them all and in order. Which is the outlier? 46. These are very common sizes as well. And so is 46 when I send them. Not because I'm writing a lot. How does the outlier affect the mean, median, and mode? So, mean, when the outlier is in there, the mean increases. The median increases. Okay. Now, I didn't calculate the mean, but it pulls it significantly, y'all. The mean might now be around 10 instead of, I don't know, 2.5. The median goes from having 9 terms and having the thing be 2 to now having the median be 2.5 because it's halfway between 2 and 3. So median increases. Now the mode, well, the mode was 2. And whether you have the 46 or not, the mode is still 2. The mode stays the same. So how about with the outlier? With the outlier, the mean increases, the median increases, and mode stays the same. There we go. Okay. Part B, describe one possible explanation for the outlier. Why do my emails ever get that big? You're sending attachments. You're sending files. There are files that are going in your thing. So when sending an attachment, the outlier could exist. Now the thing is, generally there are a lot of email servers that limit your attachment sending to about 25. Oh, these are kilobytes, not megabytes. Oh, these are small emails then. These are really small. I thought these were in megabytes. Those are really small. Okay, this is actually a typical email size, I'd say. No, wait a second. Never mind. These are normal. I'm thinking of my attachments. My attachments are normally the size of a megabyte and things like that. But every so often, I get like I have a big Photoshop file, some sort of PDF that involves images and things like that. They can get large, and they can say it's exceeding the file size. 46 kilobytes is fine. That is still tiny. 46 megabytes, about 1,000 times more. That probably couldn't fit in an email. Number 17, analyzing data. The scores of 2 golfers are shown. Find the range of the scores for each golfer. Compare your results. Now we're talking about measures of variation when we refer to range. Now, they're only asking about ranges, so I'm actually not going to copy these down in full. I'll go ahead and bring these things over, but what we do need, if you wrote them in order, we're looking for range, the maximum, and the minimum for each, okay? So, for golfer A, what are these? These are scores. For golfer A, their lowest score here is in the 80s, 83. I think it's 83. And their highest score, looks like it's in the 90s, looks like it's 98. Let me know if you see anything different, but I believe that's it. The range equals 98 minus 83, which is 15. So golfer A has a range of 15 in their scores from lowest to highest. Golfer B's range, their lowest is in the 80s as well, 87, 87. And their highest, 95, looks to be 95. So their range is 95 minus 87, which is 8. Compare your results. The range in golfer A has a greater range. That's the comparison. That's not a for better or for worse. They have better scores. You might know that golfers' lower scores are better than higher scores. So they have an 83, whereas their lowest is an 87. And remember, range has nothing to do with measures of center. We didn't get their mean, median, and mode. So a range of 15, that's not good or bad. It's just nothing. It does show that there's more discrepancy from their best score and their worst score, and that's a description we can talk about. But it says nothing about their scores when we look at range alone. Number 18. The graph shows a player's monthly home run totals in 2 seasons. You're talking my language. Find the range of the number of home runs for each season. Compare your results. Now, I don't know if you can tell based on, they're not necessarily different colors. They're both kind of beigeish, but one's lighter than the other. So in their player's rookie season, the lighter ones in the month of April, notice how these goes by 2s, any half marks are ones. So for this player in their rookie season, what are we doing? Finding the range. I'm just going to list off. We're not adding them. I actually thought we were going to add them. They had 1 in April, none in May, 6 in June. Summer seasons, they tend to hit more when they heat up and the weather heats up. July 0 to August 0, September 3. In their this season, current, 4 home runs in April, 6 in May, 4 in June, 8 in July, 7 in August, 13 in September. Now, did I need all that information? No. Honestly, with the bar graphs, I could have just looked at low and high and used those ones, and I probably should have. I want to make sure you know how to interpret this thing, though, specifically as the set, so I didn't write anything down. Obviously, I didn't write them in order. But, given that, the range for their rookie season is from highest minus lowest. Their highest was 6, their lowest was 0. Their range from any 1 month, 6 homers, as the difference from their lowest and highest amounts. Their current season, this season, their highest was 13 in September. Jeez. 13 is their highest, 4 is their lowest. 13 minus 4 equals 9 home runs. So a larger range in their current season versus their rookie season. Compare your results. The range for this current season has a greater range. This season has a greater range. Now, again, greater range isn't necessarily a good or a bad thing. And in some cases, it's bad when it comes to consistency. You can't really predict what they'll do as much. Doesn't mean that they hit more or less, although they hit significantly more. But, yeah, let's keep it in mind. Okay, in exercises 19 to 22, find the range and the standard deviation of the data set. Okay, standard deviation takes a while. We'll get to that on a per problem basis. Thankfully, they kept the numbers relatively low. Excuse me. I have to probably take care of these hiccups in a second again. Got my water ready just in case. Okay, I'm going to go quickly with range here, y'all. Range, highest minus lowest. Highest is 60, lowest is 35, your range is 25. This is without context. Standard deviation. This takes a lot to do, okay? Now, they went on a table basis, and I don't blame them doing that, but we're going to start with average, X bar. Let's average these. 40, 75, 120, 175, 235. 235 over 5 is 47. Your average is 47. What we have to do is subtract these numbers from 47, square them, add those results, divide by the number of terms there are, and take their square root. Now, that's why they do a table set. I'm going to, I don't know if I want to do that each time, because I can do a lot of that. I won't do all of it mentally, but I can lay it out without having to spend time organizing everything necessarily. And I especially don't want to write too many headers here. But your numbers to begin with were the original x's, if you will. I don't know if they say x sub n or just x. And x bar, here's x minus x bar, and x minus x bar squared. These are the numbers that we'd have to add together ultimately after we find those values. So the average is 47. We compare our numbers to 47 each time by subtracting our number with 47. So 40, 35, 45, 55, and 60. Okay. 40 minus 47 is negative 7. Negative 7 squared is 49. Positive. All of these will turn positive. 30 minus 45, 35 minus 47 is negative 12. Negative 12 squared is 144. 45 minus 47 is negative 2. Negative 2 squared is 4. And this is 8. 8 squared is 64. And this is 13. 13 squared is 169. I'm using the calculator to get that total. 49 plus 144 plus 4 plus 60. So those add to 430. So for the standard deviation, we're adding all of those up. They add to 430. We divide by the 5 terms that there are, and we take their square root. So what we get inside the square root portion is the variance. 430 divided by 5, I believe, is 86. Is that right? Square root of 86. Square root of 86 is a little more than 9, probably 9.3 or something. So 430 divided by 5 is 86. Square root of 86, 9.27. Let me show you on the calculator here. 9.273. I think they rounded to the nearest tenth for some of these situations, so I'm just going to say 9.3 is my le standard, la deviation. Now, I'm not going to get too deep into what that specifically represents. That being said, the lecture portion, I do cover it, but that's your standard deviation. It's another form of variance. It's a better form of variance to talk about than range as an overall, variation to talk about other than range. It's just it takes longer to do. There's a way to have your calculator do it as a whole and say, hey, give me standard deviation of these, but we're computing using formulas here. All right, number 20. Now I get to speed up as I go, given that things work cleanly in our favor. Because these numbers are larger, I don't know if it's going to be faster or slower. And there are more numbers. Okay, range. Smallest number, are these in order? Oh, not quite. But the smallest number looks to be 116. I thought this said 114. 116 is subtracted from the largest number, which is 1. I need to look at the printout. 135. And that's 19. Wait a minute. Is that right? 135. Oh, 141 is the largest. I was going to say, is that right on the calculation? And then I just saw that that was a different number. 116. All right, that's 25. All right, range is 25. Standard deviation. Let's do it again. We got to average these first. I'm going to do this on the calculator. So I'm going to add 141 with 116, 117, 135, 126, and 121. I'm getting 756, and we're going to divide that by 6. I believe that is 720. That's 120. 126? I'm going to confirm that. Divided by 6. 126, yep. So there's your, that's not your standard deviation. That's the mean. Standard deviation is taken by subtracting these results from there. So given our x's that we have, I'm going to skip that middle part of the what x bar is because we know we're subtracting 126 each time. I'm just going to subtract them there, and then we're going to square them here. No need to rewrite that over and over. So our x's, we got 141, 116, 117, 135, 126, and 121. All right, a lot to do here, yeah? So now there is a way you could type this all in the calculator in one shot, and I might do that for number 21, all right? I'll show you how to do it in one shot. You got to type a lot, and you got to make sure you have your order of operations down. But 141 minus 126, that's 15. 15 squared is 225. 116 minus 126 is negative 10. Negative 10 squared is 100. This one is negative 9. Squared is 81. This one is, oh, I guess these aren't too big. 9 squared is positive 81 as well. This is 0. 0 squared is 0. That's awesome. And this is negative 5 squared is 25. Let me try this one in my head here. That's 250, 350, plus 162 is 512. So these add to 512. We're dividing by 6 terms? 6 terms. I'll let the calculator do the rest. So 512 divided by 6 is 85.3 repeating. We're going to take the square root of that variance value. And we're getting 9.2. Was the last one 9.2? Last one I put 9.3. I think this was 9. This one says 9.237. I think the last one said 9.27 or something like that. So very, very close to each other. But 9.2 versus 9.3. Given that the numbers have nothing to do with each other, boy, their measures of variation are very close. And remember, the range was 25 on the other one. So these were so close in range. And standard deviation, again, virtually identical. Yet the numbers were so different because they're just describing how far away the points lie from the mean and how far away the min lies from the max. That's it. They're not talking about their center. These mean, median, mode values, whatever, would be so different from numbers 19 and 20. But the variation, very similar with their respective values. I don't know if they meant to do that. Number 21. 1.0, 1, 2.0. Puh, those are just 1 and 2. All right, the range. The range is, the highest looks to be 2.5, and the lowest is 0.5, unless I mess something up. So that range should be 2. The standard deviation, let's get that mean. 2.5, 5.5, 2.5, 5, 6.5, 7.5, 9. We're doing 9 divided, is that 6 values? 9 divided by 6, okay. And that's 1.5. That's not the answer. Oh, I'm sorry. This is x bar. This is your average. X bar equals, okay. Sorry about that. That looks a little weird. Now, you could do this all in one set right here. Whether I said I was going to do it on the calculator. Instead, I'm just going to show you in this way how I'm going to do it. I'm going to do 0.5. I'm going to do these numbers minus 1.5 and square them. So 0.5 minus 1.5 is negative 1. We got to square that. 2 minus 1.5 is 0.5. We're going to square that. 2.5 minus 1.5 is 1. 1.5 minus 1.5 is 0. 1 minus 1.5 is negative 0.5. And 1.5 minus 1.5 is 0. This is all over 6 inside of there. So we're subtracting those, squaring those, and taking the square root. I can probably do most of this without the calculator. I just did some of it without it. This is 1 plus 0.5 squared is 0.25. A quarter. Plus 1 plus another 0.25 there, all over 6. So yeah, this can kind of, I have to use the calculator at the end. This is 2.5 over 6, which is, something. So I'm going to let the calculator kind of do the rest for me. 2.5 divided by 6. And then the square root of that value. 0.645. I'm going to use 2 decimal places this time. I'm going to say 0.65. 0.65 is my standard deviation for that one. Okay. Number 22. 8.2, 10.1. This time I think I want to go fully in the calculator on the standard deviation portion. It's going to type a lot, or it's going to take a lot to type, but once we have it, we're done. We do have to get the mean first, though. Okay. 2.6, 4.8, 2.4, 5.6. Okay, that range, though, we're looking at 10.1 is the biggest. Is 2.6, 2.4 is the smallest. Is going to be 7.7. The standard deviation, let's find the mean. I'm going to use the calculator for that, so I'm going to have you watch me. We're going to do 8.2. Okay, I think that was 8 numbers. Divide that by 8, that's 5.5. Divide that by 8, we get 5.5. So that's the mean value. Now, I'm going to write that over here. But the rest I'm going to do in the calculator, okay? So check it. We're going to do this minus this squared, plus this minus this squared, plus this minus this squared, etc. all the way to the end. That'll all be in the numerator. We're going to divide by 8 as a whole and take its square root. Now I can do that all in one single step by this. I start with square root. And in the numerator, open parentheses, I now have to do another set of parentheses. This is why you don't want to do it this way often. I can do it just fine. I'm going to be fine with it, but it's just a lot to do. Do these squared. Boom. And I'm still in the numerator. So plus, this probably isn't faster. 10.1, I just want to do a little less writing. 5.5 squared. If you know these differences, then you can do that part a little bit more easily. But I want to show you just in this way. 2.6 minus 5.5 squared. The mean's the same each time. Plus 4.8 minus 5.5 squared. Plus, and it's easier not to do it on a computer. 2.4. I want to make sure I'm not typing any numbers wrong. That would suck. Minus 5.5 squared. Plus 5.6. I know what 5.6 minus 5.5 is, but we're doing this all as one. Plus 7.0 minus 5.5. I'm going to be as literal as possible for this. Squared. Plus 3.3 minus 5.5 squared. Okay, don't press enter yet. That is the end of the numerator. Let's close off the numerator with parentheses. Now I divide by 8. And if I close this last set or not, doesn't matter. This is all within the square root. This will give me the answer. This is standard deviation, point blank, done. 2.599, so I'm going to put 2.6. So my standard deviation for this guy here is around 2.6. Now, I did a lot of work on it. I just didn't write it down, but I did compute it. If you want to see my work, it is right there. There's my work, homie. Okay, cool. Number 23. Analyzing data. Consider the data in exercise 17. I got to look back at where it was. All right, let's copy. Oh, we have that on over here. Number 23. The number 23. It's all over the place, man. It's all over the place. Okay, there's a movie called The Number 23. It's a movie with Jim Carrey. It's not a comedy. I mean, you can laugh at it if you want to. It's not meant to be funny. It's supposed to be like a thriller. It's something where the guy obsesses basically over the number 23. He sees it everywhere. He sees it everywhere, right? Sorry about this. I just want to talk about this really quickly. And I knew this from the trailers. He's like, look, these things here, there are 23 letters in this thing, or whatever it is, like a bunch of stuff, right? He's just obsessing over it. It kind of, I forget what it spirals him to do. It's more like he becomes a killer or something like that, right? Something weird. In one of the very first scenes, maybe the very first scene, I can't remember, he's doing Jim Carrey things, whatever, and there's a dog that comes up to him, and he's like, oh, hey, and he looks at the dog collar, and it says, Ned. Ned, first thing I start to do in my head is what? N is the 14th letter of the alphabet, E is the 5th letter of the alphabet, D is the 4th letter of the alphabet. 14 plus 5 plus 3 is 23. I knew it right off the bat, right there, right then and there. And I forget if they disclosed it later. I think they did. Or if it was an Easter egg, but they did it much later, where in the very beginning I was like, I got this, boom, I see 23 as it is. I don't know what I wanted to say with that. Oh, and I think if they did do it later, it was like much later, like a revelation, where Jim Carrey's like, oh, NED, it has the 23, oh my gosh, things. And I hit number 23 in every problem set that I do, and for some reason on this one, I wanted to talk about it, because we're talking about stats, I guess. How everything relates. Okay, guys, here we go. Number 23. Consider the data in exercise 17. Boom. Find the standard deviation of the scores of golfer A. Interpret your result. All right, well, we got to do that again. Did we do the mean? No, we just did the ranges, right? So golfer A, standard deviation is what we're going to do here in a moment. For part B, do it for golfer B and compare the standard deviations. What can you conclude? Okay, so for golfer A, we need to get the average. I'm gonna do this with my calculator. Give me one sec, right quick. 83. Oh, hold on a second. 83 plus. Okay, when you add them, you get 900. Okay, divided by 10 is 90. So 900 over 10 is 90. That is their average score. Now, their standard deviation, I am going to do this a little bit quicker as a whole. We are adding the sums of the squares of the differences, or the residuals, the differences of their score with the average. 83 minus 90 is 7. 7 squared is 49. 84 minus 90 is negative 6. Sorry, negative 7. Negative 6. Negative 6 squared is 36. So we're adding these up. 91 minus 90 squared is 1. 90 minus 90 squared is 0. I'm going to actually leave it out. 98 minus 90 squared is 64. 88 minus 90 squared is 4. Because it's negative 2 squared. Remember, all of them turn positive. 95 minus 90 squared is 25. 89 minus 90 squared is 1. 87 minus 90 squared is 9. 95 minus 90 squared is 25. So there are parts you can speed up a little bit more than the whole table thing. We are still dividing by 10. Even that 0 counts as one that you add in. I just kind of ran out of room. So let me add those up. 49 plus 36 plus 1 plus... Okay, divide those by 10. I get 21.4. Take the square root of that. Somewhere between 4 and 5. 4.6. So my standard deviation here is around 4.6 for golfer A. Golfer A. So golfer B, standard deviation here. Oh, their average. We have to get their average. X bar for golfer B. We add these, so give me a moment. This is why this thing's going to take a while. Plus, I'm telling stories about polar bears, the number 23. I choose to use my time as I'd like to, and this is my form of entertainment. Sue me if you don't like it. I hope you do, because this is how I need to keep myself a little sane when I'm doing these things instead of obsessing over number 23. 910 over 10 is 91. Very close averages between the two. We talked about how the ranges are different. Let's see how their standard deviations differ, though. I'm going to guess golfer A is a larger standard deviation because of their spread of their lowest and highest values, but that's not always necessarily the case. Because maybe there were outliers. I don't think there were. So I'm going to guess golfer A does have a higher standard deviation. So standard deviation of golfer B. Let's check it out. 89 minus 91 and squared. Let's see. I actually can't see those numbers. Let's move it down a little bit there. Okay. So square root of. All right. 89 minus 91 is negative 2. Squared is 4. 93 minus 91, 2. Squared is 4. 92 minus 1 squared is 1. 88 minus 91 is negative 3. Squared is 9. 89 minus 91 is that 4 again. Or 2 squared is 4. 87 minus negative 4 squared is 16. 95 minus 91 is 4 squared is 16. And then 9, 0, I'll just put it there, and 1. Again, we're squaring the difference between those values. Hopefully it's making sense why I'm doing that a little bit faster there. I'm going to do this one in my head here. 4, 8, 9, 18, 22. Were these numbers bigger? Those are significant. This is going to be a much bigger standard deviation. Okay, I lost my train of thought here. 4, 8, 9, 18, 22, 38, 54, 63, 64. So square root of 6.4, 64 over 10. That's going to be somewhere between 2 and 3. Square root of 6.4 is 2.5 about. Significantly smaller standard deviation. It says compare the two. The standard deviation for, compare the standard deviations. Hold on, I didn't call this part A and part B. So part A, part B. Part C, golfer A has a larger standard deviation. So their scores are more spread out. Right? That's standard deviation just explains how far your numbers are from the mean as a whole in both plus or minus realm. And this one has more spread. The number 24. Consider the data in exercise 18. We're going to do the same stuff as we did before. This is the rookie. This is the baseball stuff. Did I copy and paste? I got to get the image. Give me 1 second. Oh, it's at the top of the page here. So let me bring this over. Oh, you know what? I wrote down the numbers. Let me do that. They are right. Oh, number 18. I was looking for 24. They're right here. Here we go. Well, I was looking for this, and I'm like, I can't find it. Let's find number 24. All right, so here are the numbers. So for number 24, much smaller numbers are just easier to deal with in general. I know that for the most part, we're having a lot of things to do on this stuff, but just bear with us when we do it all. All right, find the standard deviation of the monthly home run totals in the player's rookie season. So standard deviation for rookie season. Oh, start with the mean. Mean for the rookie season. And again, I'm going to go faster if I can. You add them up and divide by how many there are. 1, 7, 9, 12. 12 over 6 is 2. He averaged 2 home runs a month in his rookie season. Even though he only hit 2 once, that was his average. So there's his average. Standard deviation in his rookie season. We're going to take the difference between these and the mean and square them. 1 minus 2 is negative 1 squared is 1. 0 minus 2 is negative 2 squared is 4. 6 minus 2 is 4 squared is 16. 2 minus 2, 0 squared is 0. 0 minus 2 squared, 4. And then 3 minus 2 is 1 squared is 1. Divided by 6. 1, 5, 21, 25, 26. 26 over 6. And I'll just go from there, because that's going to be some sort of repeated decimal. So square root of 26 over 6. Now, this is kind of weird to talk about these as a whole with what this stuff is doing, but this is around, it says 2.08. 2.081. I'm just going to put 2.08. It's weird to talk about as a whole, given this stuff, because it's of such a small sample size. It's really weird to work off of, and 6 almost serves as an outlier for these numbers. I would kind of say it does. It really pulled the mean up from what it was. I think it pulled the standard deviation a lot in general as well. I almost called it an outlier. Part B. Excuse me. Standard deviation of, not B, current season. I'll put a C here. The mean of the current season, rather. 4 plus 6, 10, 14, 22, 29, 42. 7. So on average, they got 7. Look, that's really pulled up by the 13. They hit 7 once. Oh, they hit 8. Is that right? That seems low. Let me do that again, just to make sure. Maybe it's right. I don't know. 4, 10, 14, 22, 29, 42. Divided by 6 is 7. Okay. It seemed low when I saw that all these were kind of close, but okay. Standard deviation. Okay. I need to bring these numbers down, I think. I need to see them. Okay. 4 minus 7, negative 3 squared is 9. 6, 1. 4, again, is 9. 8 is 1. 1 squared. 7 minus 7 is 0. 13 minus 7 is 6. Squared is 36. Divide that by 6. Okay. This will become much more spread out based off that. 10, 20, 56. Not much more, but it will be more. So square root of 56 over 6 is 3.06, 3.055. So around 3.06. So there's more spread. They're more distributed and more spread out in their current season. So their current season, part C, has a higher standard deviation. So that means their home run numbers are more spread out. That means this is given the months, a little less predictable to find out what they're going to do, despite the fact that they have higher home run totals. It was that last month that really did them in. All right, next exercises 25 and 26. Find the mean, median, and mode of the data set after the given transformation. Now, we have to take exercise 5 and increase each value by 4. So that does mean we have to go back. I wonder if it's easier to use their values or what. So number 5, okay, I wrote them down. Let's just take what they have and let's add 5 to each of them. So this is number 25. So number 25. So increase number 5 by 5 each. You know what I'll put? Oh, never mind, that's fine. By 5 each. Okay, so on number 5, you can see I'm going to do 3 plus 5 and make it 8, 5 plus 5 and make it 10, 1 plus 5 and make it 6, etc. 10, 6, 6, 7, 8, 20. Now, I'm not as inclined to do it this way as often, okay? I want to make sure you know that. I have to rewrite them in order now, unfortunately, as well. But the mean, 18, 24, 34, 40, 46, 53, 61, 81. Is that 8 numbers? No, it's 9 numbers. 81 over 9 is 9. The median, not written in order. This is why I kind of want to go back to the previous things we had. We got 6, 6, 6, 7, 8, 8, 10, 10, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9. 8's the middle number. The median here is 8. So 9, 8, and mode. 666 is 6. What are the questions? Because they said compare, I'm sure. Oh, wrong set. Find them after the transformation, the mean, median, mode. Oh, they have to increase by 4. I was thinking when I said this, I was going to say, did I just write 5 because it was number 5? I'm sorry, guys. Did I write number 5 because it was 5, or was that the number? And I was thinking, let's go back and check. I'm like, no, I think it was a 5. No, I wrote it because it was number 5. Okay, well, everything's going to change a little bit, but here's the thing. Now it's a good time for me to bring this up. I'm going to bring it up now, so I'm not really going to recalculate, but I have to change these answers, obviously, right? Okay, what were the original mean, median, mode? This is 9, 8, and 6. Remember those numbers, 9, 8, and 6. Let's go to number 5. Previously, they were 4, 3, and 1. Let's look at 9, 8, and 6 versus 4, 3, and 1. What happened? 4 plus 5 is 9. 3 plus 5 is 8. 1 plus 5 is 6. They all got 5 bigger when I made them 5 bigger. So what I'm going to do in future problems, especially when I compare to numbers they already have, I'm going to just do that when asked. So on this one, instead of, and I apologize for what I did, my bad, but these things right here, we increased by 4 each. Very, very sorry. Very, very sorry. The mean here, you take what it was before. It was 4 before. 4 plus 4 is 8. The median before was 3. Well, 3 plus 4 is 7. The mode before was 1. Well, 1 plus 4 is 5. You add 4 to each of these values, they become that much bigger. Very sorry about that. All right, number 26. Each data value increases by 20%. Now these ones, you make them 20% larger as well. So this time I'm not going to rewrite the data. I'm going to take the answers that I got and I'm going to increase them by 20%. I already did the problems. Why would I do it twice? So just taking everything we got on number 6, besides writing 6 itself. Let's kind of play off that. It's that number 23 that haunts me, man, to this day. Here's number 6 values. Okay, so the mean. Oh, where did my mean go? It didn't copy over. The mean was 12.6. Okay, so the mean was 12.6. The median was here. The mode was here. All right, the new mean for the new one is going to be 12.6 times 20% increase, by the way, is 1.2. You might remember that from some word problems thing we would have done in the past. So 12.6 times 1.2 is 15.12. This is our new mean without increasing every value by 1.2. There are only 5 of them, but I'd have to recalculate them, and I don't want to do that. Median. I don't want to. Really, I shouldn't have to. Median, 12 times 1.2. Isn't that 1 point? Yeah, 14.4. So 12 times 1.2 is 14.4. Mode, there's going to be no change. There's still none. You can't multiply none by 1.2 because there's no change in frequency, right? If there was, whatever the mode was, you'd multiply by 1.2. If there isn't one, there's not going to be one now. So there it is. Okay, 27. More transforming data. Find the values of the measures shown when each value in the data set increases by 14. Now, mean, median, and mode are considered to be measures of center. Measures of center increase with the data increasing by 14, increasing by adding k to them. So the original sets, I'm just going to go ahead and copy and paste these things over, and then I'm going to show you your changes here, right here in front of you. I hope that's okay. So mean, median, and mode will change. You are going to do the addition of 14 to those ones. Mean, median, mode. 62 plus 14 is 76. 55 plus 14 is 69. And 49 plus 14 is 63. Those are the new mean, medians, and modes. Range and standard deviation do not change. do not change. It's still the same range as it was before. Still the same standard deviation as it was before. No change on those. So that's how I'm going to kind of work those ones a little bit fast on it. Because we don't have the actual data, so they're saying, hey, how does it work? That's how it works. And maybe that's what they wanted you to kind of... Like, so for the previous problems, maybe they actually wanted you to go back to the numbers, recompute them. Now they're saying you don't actually have the data and tell us how it works. And so did I speed up through 25 and 26? Maybe a little bit, but I screwed up on 25, so I didn't want to do it twice. Number 28, find the values of the measures shown when each value in the data set is multiplied by 0.5. That means they are halved. When you multiply something by 0.5, all the data is halved. What does that mean for these values? It actually means all of them are halved. That includes the measures of variation. Everything gets divided by 2. So the new times 0.5 is divided by 2. So all these divided by 2. Mode will still stay as none. There's still no change in mode. This is 160, 150, none, 105, half the range that it was, and half the standard deviation that it was, 35.3. Yeah. So we'll get those ones there. Still no mode. No mode. Number 29. How long have we gone? Hour 50? Yeah, it's been a little while. We're not even 2/3 of the way done, or 3/4 of the way done. Error analysis. Describe and correct the error in finding the median of the data set they say the median is for. Now, I can't guarantee that they are wrong, but I can say what I believe that they did, which is they found the middle value, but the numbers are not written in order. So my guess is whether or not they're right, or whether they're right or not, their approach is incorrect. They found the middle value of an unordered set. So in correcting it, the answer must not be 4. Otherwise, that just makes you feel bad. Let's write them in order. 2, 3, 4, 4, 6, 6, 7, 8, 8. I'm going to have to check that. I think so. I think there are 9 numbers. The middle value in this case is 6. So there is our median from that. I think I did this in the first problem, but teachers would often recommend that you cross out values as you go. And I'd agree. Write them first in whatever order they have them and cross out values as you go so you know that you've taken care of all of them. 2, 3, 4, 4, 6, 6, 7, 8, 8. And then you have your new list written in order to work off of. That's probably sorry, my computer is kind of buzzing. Okay, it's not right now. That's kind of the go-to to me when you want to write them in order. Number 30, describe and correct the error in finding the range of the data set after the given transformation. Add 10 to each value. What does that mean? I don't even know what that means, so... Oh, after the transformation. Okay, I got it. I thought they said, here's the list. To find the range, we're going to add 10 to each value. They said, here's the problem. Take this data set and add 10 to each value here, and what's the range? So what they did was they took what is the correct original range. Their range goes from negative, these are written in order. They go from negative 13 to 13. So they are correct. I'm going to tell them what they have correct. The range is 13 minus negative 13, which is 13 plus 13, which is 26. So they have the right value in their original range. However, so while their original range is correct, their new range after the transformation of adding 10 to each value changed when it shouldn't have. If I add 10 to each value, negative 13 turns into negative 3, and 13 turns into 23. Do you know what 23 minus negative 3 is? It's still 26. The range doesn't change. Range is still 26. Range is still 26. Now, if you doubled your values or whatever, You double your range. It would be 52. Because now the smallest value is negative 26, biggest number is positive 26, and 26 minus negative 26 is 52 if you multiply by a value. But if you're adding or subtracting a number, no. Okay, number 31, problem solving. In a bowling match, the team with the greater mean score wins. As average. Not like grr. Oh my gosh. She's not mean. The scores of the members of two. Imagine being. Okay, I wondered. Sorry about this. It's probably a stock photo, I'm not sure, or they took a photo for the book. But does she know, hey, we're going to take a photo of you, and it's going to be for a math textbook. I got to check the publishing kind of things and what credits they give. Or they pull this photo out, and they're like, we're going to put this in the book. I feel so bad for her in a way. Now she's, moment of ridicule, and now living on my YouTube channel. She probably has the higher score, though, so we'll see. Okay, in a bowling match, the team with the greater mean score wins. The scores of the members of two bowling teams are shown. Which team wins the match if the team with the greater median score wins? Is the result the same? Explain. Okay, I copied it. I'm going to paste that. All right, team A, team B. Now, here's the thing. Technically, for average, because they played the same number of games, just the total itself would also guarantee the victor, meaning the team with the greatest sum wins, period. So for team A, if I add 172, 130, 173, and 212, I get 687. So for the average of team A, we're going to divide, I don't know why I wrote it 2. We're going to divide 687 by 4. And for team B, 136, 184, 168, and 192. We're going to take 680 and divide by 4. Now, here's the thing. Team A won because they have a higher sum. Doesn't matter what the average is. I don't need to technically divide by 4 if they played the same number of games, if they had the same number of points. But let's get the averages anyway. That's what they want. That's a part of what we're doing as a whole. This is 171.75. Try not round that. That's exact. And this is 170 exactly. So team A wins. This is part A, by the way. Team A wins because they have a higher average. Now, if we did median, rewritten in order, this is 130, 172, 173, and 212. This median is, I didn't get the median yet, but written in order, I have 136, 168, 184, and 192. So this guy's median is based off the average of these two. Oh, let me just write it down below. But the average of 172 and 173 is 172.5. So the median of A is 172.5. The median of B, we have to average 168 and 184. Half the distance between those is 176. So you average them, you get 176. Team B wins if you refer to median. So team A wins with mean. Team B wins with median. I wish these are different questions, like part A and part B, because this is hard to distinguish these different parts. Team B wins with median. Who would ever do median in a bowling thing? That's too stat heavy. Part B, which team is more consistent? Explain. Consistency is going to have to do with lesser variance, whether you're talking about range or standard deviation or whatever you're referring to there. You really want to look at those. So team A has a range from 212 to 130. Team B has a range from 192 to 136. Or, sorry, 130 to 212. So let's see. The range for A is going to be 212 minus 130, which is 82. The range for B is 192 minus 136, which is 56. So this is a bigger range. Already you're probably seeing this as less consistent. Now, the tricky part is on standard deviation, which I don't want to overly calculate really unless they actually ask us to do so. Once I see that range, I'm already seeing that range A is a less consistent team from range. 172 and 173 are very cool. Actually, I don't know what the mean is. Oh, I do know the mean. It's 171.5. They are very close to the mean. And I can see where that lack of spread there can help you out. But these two are outliers from the mean by so much that those squares of values, all that stuff, those will really separate it. I believe the standard deviation will be there as well. I'm going to say Team B is more consistent based off range alone. I'm sure that standard deviation will be closer as well. Team B is more consistent with a smaller range, and I'm just going to guess this, and standard deviation. It's unlikely that they would ask a question, which one's more consistent, and it has a smaller range and bigger standard deviation. How do you answer it? How do you answer it? I might err toward the one with the smallest. It depends on how much they change by. This is a significantly lesser range. I mean, that's much less, so they're much more consistent, staying within their amount. Even if they lost, they're more consistent. Part C. In another match between the two teams, all the members of Team A increase their scores by 15, and all the members of Team B increase their scores by 12.5%. Which team wins this match? Explain. Okay, we're going by the means. So the mean for Team A in the new one, in this one here, we have to take 171.75. And because measures of center increase with the score thing, we get to add 15 to it, and we get 186.75. I like these questions. Team B's average will take 170, and it's going to increase by 12.5%. That means you multiply by 1.125. 170, I don't know this answer. 170, I'm not saying I don't know the calculation, I'm saying I don't know who wins. 170 times 1.125 is 191.25. That's a new greater average. I don't know how they all increase by the exact same amounts like these things work, but mathematically, Team B is victorious. Number 32. Your friend, who's probably wrong, your friend says that when two data sets have the same range, you can assume data sets have the same standard deviation. Because both range and standard deviation are measures of variation. Is your friend correct? Explain. No. Range just uses two numbers to calculate the highest and lowest numbers, max and min. Standard deviation uses them all. That alone says if you're using different data to calculate, you can expect different answers. Is it guaranteeing different answers? No. But you can expect different answers. My friend is incorrect. Range only uses max and min, whereas standard deviation uses, I don't know why I type out the abbreviation there. I can type it in full. Uses all the data values. That alone can't guarantee sameness. Or can guarantee lack of sameness, basically. For a second, I thought their question was saying the whole thing, if you do a data transformation, right? If we add 15 to everything, because the range wouldn't change if you add 15 to everything, right? We just had an error analysis on that. Same thing on standard deviation. That wouldn't change by a data transformation. That's not what this is. They're saying when two things have the same range, are their standard deviations the same? No. You have to look at all the data for that. Number 33. The table shows the results of a survey that asked 12 students about their favorite meal. Which measure of center can be used to describe the data? Explain. You cannot calculate a mean, an average, or a median of these things here. The only one you can calculate here is mode, because you can determine the frequency of occurrence in the statistat. Mode. It is the only measure of center. It's really the only measure for which frequencies can be tracked by being categorical and not necessarily quantitative. I guess I didn't have to say the frequencies portion of it, but the idea is you can do it because you're tracking frequencies only. I don't know what the answer is. I see spaghetti twice. I see pizza 3 times. I actually didn't see any repeats the first time. So steak once, chicken. Oh, no, you don't mention steak. Steak once, taco, chicken, fish, chili, hamburger. Oh, steak twice. Steak twice. Okay, good on you. But pizza wins. Pizza has 3. Mode is pizza. By the way, I don't see many vegan versions of all these things. I don't see vegans being very included in this set when you consider the generic types of things that were not generic, the default versions of what we would say for those. Sorry. Maybe chili. They didn't ask many vegans. 34. The dot plot shows the ages of the members of 3 different adventure clubs. This is very symmetric. Actually, it is symmetric. Without performing calculations, no calculations. Which data set has the greatest standard deviation? Which has the least standard deviation? Explain your reasoning. Standard deviation is about how far your points spread from your mean. Listen, all of these have the same mean. I'm not calculating anything. I'm not calculating standard deviations especially. But the mean and the median and the mode, mean, median, and mode for all of these are 15. Averaging these gets 15. I just know because the symmetry. And 15 being in the middle. Median, literally 15 is of the middle value in frequency. Mode, it's the most frequent. What was I saying with this? Oh, they all have the same measures of center, but they have different measures of variation. This one has a range of 4. This is a range of 6. This is a range of 2. This is a standard deviation that's in the middle because falling from the mean, these numbers don't fall from the mean as much as this, and these don't as much as this. This one falls most from the mean. Is the greatest standard deviation. So, number 34, how do I see it? Greatest standard deviation is graph B. Least is graph C. Most spread in points and least spread in points. That's a smaller way of me saying what I stated in full out loud. All right, number 35. Reasoning. A data set is described by the measures shown. I like how the later problems are quicker. There was another section I think I had that where the later problems were good, and I really like that. There were probably, I say that too soon, there were probably some long questions after. Find the mean, median, mode, range, and standard deviation of the data set when each value is multiplied by 3 and then increased by 8. Okay, so I'm going to copy and paste these, and I'm going to I'm going to have to do them again because there's too little room for work. There's too little room for work. So there's the originals. The new mean. Actually, I'm going to write the work here, though. I'm just going to write the answers down below. We are going to triple all of our values. Everything. We do multiply by 3, and then we add 8. But remember, measures of center get the increase in addition. Measures of variation do not. So this is where they end. So new mean is 27 times 3, which is 81, plus 8 is 89. New median is 32 times 3, which is 96, plus 8, which is 104. New mode is 18 times 3, which is 54, plus 8, which is 62. The range, you only triple, you do not add 8. 41 times 3 is 123. And the standard deviation, which I could have used sigma for. Standard deviation is 9 times 3, not plus 8, which is 27. That's it. Number 36, critical thinking. Can the standard deviation of a data set be 0? Can it be negative? Explain. It can be 0 if all your data is the same because there's no spread. The standard deviation is 0 if all of your data is the same value because there is no variation. It can't be negative. I'm not going to get too deep into why, but here's the thing. Your standard, actually I can get into why, but it's not a logical reason, it's a mathematical reason. And then I'll talk logic kind of behind what standard deviation actually does. But it can't be negative because the formula itself, you're squaring values, and eventually you take the square root of values. So we can't take square roots of negatives and get real numbers. And when we square numbers, they turn positive. So it can't be negative mathematically because we square numbers and then add them, meaning all must be positive or zero, all positive or zero. And we take the square root, can't take square roots of negatives. So that's a mathematical reason that we have that. But I'll tell you really why it is, not why it is, but when we do standard deviation, if I get a standard deviation of 3, it actually already is, how do I say it? It actually already is something that you add and subtract. That standard deviation of 3 is what you add and subtract from the mean. So although there's no negative in the value, you still use it in a negative fashion. If my mean is 80 and my standard deviation is 3, I'm going to add and subtract 3 from 80. Plus 3 is 83, minus 3 is 77. One standard deviation away from the mean has a range from 77 to 83. So you do still use it in that way, even though it's not negative. It doesn't matter that it's not negative. You still use subtraction with it. So there's that. Anyway, mathematically, there would be why that is and how that is. Excuse me. All right, 3 more questions. Number 37. Using tools, measure the heights in inches of the students in your class. I am not doing that, but I will let ChatGPT do it. Let me... I'm not going to pause the video and say, hey guys, I'll be back tomorrow. I'm going to measure it. And yeah, I'm going to actually ask them. I could poll them, but I wasn't actually prepared for this question. So I'm going to ask ChatGPT to give me a second here. Let me pop this thing up. Google Chrome. And here. Okay. Provide the, wait, hold on. What do we have to do with them? I'm not going to do standard deviation of 30 students. Oh, that's a lot. Provide the heights in inches. I'm going to do 10 in inches of 10 random, I'm a high school teacher, of 10 random high school students. Yeah, that's it. All right. Now, did they say do it in inches? Because that's, yeah, I'm going to do it in inches. A new student 7 feet tall joins your class. Okay, sorry. I'm reading the question later. It's quite an interesting one. Okay. Write it out. I'm going to have this help me. Whoa. Oh, shoot. I closed the window. Oh, my goodness. Hold on. I have to pop it up again. Give me 1 second. You can read this question thing as it works. I must have hit Control W or something like that, which closes your tab. Don't do that. I'll bring it back up. But look at the next question. I didn't see the full thing, but I just saw a 7-foot person enters your class. All right, I lost my window, so let's bring it back up. Okay, I'm gonna have this help me a little bit. Arrange the heights in increasing order as a list separated by commas. I use AI all the time to help me in math. Not like math, like things like this. I let it systematically help me here. Not get answers, but provide me needed info. AI has its uses, absolutely. I don't like it taking over all my Google searches and all my advertisements and things like that. I hate that. All right, these are all in inches. Okay, find the mean, median, mode, range, and standard deviation. Now, I did have it do it in increasing order. I probably shouldn't have had it help me that much, but one less thing I got to worry about. Okay, so the mean, which by the way is used in standard deviation. I'm gonna use the calculator. So 62 plus 63 plus 64 plus 65 plus. This isn't really random. I just noticed that they're all different. That's not very. It's random, I guess, but I don't know if it knew that this was gonna happen. I guess I could have told it that it could have used the same height more than once. Too late. This is what I'm using. I measured my 10 students. This is what it looks like. I wonder if I gave it 30 students, if it would give me 40-inch students and 100-inch students and things like that. Okay, I calculated the sum to be 665, if that's right, and divided by 10 is 66.5, I should say. That is the mean. The median, and I know I wrote mean as x bar. Mean, there. The median, there are two middle values of 66 and 67. By no coincidence, this one is also 66.5 because it's the halfway value between these. When all of these are the same amount apart, like that, and whatever, you're destined to have this perhaps happen, and it did. Yeah, mean and median have the same thing because of the symmetry in spread and stuff like that. Mode, unfortunately, there is none. I screwed up with that. In a class of 36 students, you are going to have numbers appear more than once. It's not going to be the same number of numbers. They'll trend around some middle value. You will get a mode of 5'6", something like that. Whatever. Maybe it depends on the class. Juniors, maybe a little taller, freshmen a little smaller. But you will get some sort of mode. I only had 10 of them. ChatGPT really screwed the pooch for me on this. I apologize for that. Now we still have to do standard deviation and range. I'm going to do range first actually here. Range is the distance between, or the height difference between the tallest and shortest students. So the range is going to be 71 minus 62, which is 9 inches. That's the height difference between tallest and shortest student. Standard deviation, we are going to take our mean of 66.5, and I have to do a little bit of work on these ones here, but the distances are 62 minus 66.5 squared, all that kind of stuff. So I'm going to do, whoa, that is just a big standard deviation thing. The kind of nice thing about this as an overall is when I square these values, they'll kind of be the same. So you'll see what I mean. 62 minus 66.5 is negative 4.5. I got to square that. And I think I know these values too. I just want to write them out. Then you have 63 minus 66.5, which is negative 3.5. I got to square that. The next one is negative 2.5 squared, and then negative 1.5 squared, etc. And then negative 0.5 squared. That's the first 5 of them. And the next 5 are the positive versions of that, but when you square them, it becomes that same number anyway as the negative ones are. And no, this is not a fraction. This is just writing them all out. That's only from my set. Look, you're probably not asked this question unless you're asked as a class. Like, you're literally doing it as a class. You're probably not watching my video for this question anyway. Anyway, negative 4.5 squared and 4.5 squared are the same number. That's what I was making the point of. So they're both positive, whatever that value is. And 4.5 squared, I believe, is 20.25. So here's what I'm going to do. I'm going to double those. I'm going to double 3.5 squared, which is 12.25. I'm going to double 2.5 squared, which is 6.25. Not doubled, but just 2.5 squared. 1.5 squared is 2.25. Why did I write 1.5 then? 2.25, we got to double that. 2.25 doubled. And then 0.5 squared is 0.25 and doubled. Just barely fits, and divide that by 10. I'm going to try this in my head until the square root part. This is 40.5 plus 24.5. A lot of 0.5s here. Plus 12.5 plus 4.5 plus 0.5 all over 10. Okay. I wonder if this is like a really clean number. ChatGPT is like, I know what you're going to do, and I'm going to help you with it. 40.5 plus 24, that's 65. These two added together is 17. 65 plus 17 is 82. Plus 0.5 is 82.5. 82.5 over 10, that is a big square root for that, which is square root of 8.25. It's a little less than 3. Little less than 3. Let's figure that out. Now, this is open-ended, so it is whatever you calculate. 2.87. Standard deviation is 2.87 inches. Plus or minus that many inches from the mean. I said this in the lecture, so I'll say it here. Well, they're weird calculations, but if I add and subtract 2.7 from 66.5, 68% of your student stuff should fall between there. Not necessarily just these 10. This is a sample size, but of your set, if it's a large enough sample size, 68% falls within plus or minus 2.87 inches of 66.5. You add or subtract another 2.87 inches, 95% of your data falls within those two, and add and subtract another 2.87, 99.7, I think it is, percent of them falls within there. Almost all 100% fall within that range. That's how standard deviations work. I don't know how they came up with those, but that's how it works. That's just part A. Let's go to part B. A new student who's 7 feet tall joins your class. Now, first of all, 7 feet is tall, but also that is times 12 inches per foot. So that's 84 inches. So an 84-inch student joins your class. How would you expect the student's height to affect the measures in part A? Verify your answer. Verify does mean calculate. And I don't know how much I want to do that with the standard deviation. We have to remember, I don't know. I don't think I want to verify. I expect, first of all, mean and median should increase because it's pulling the information up. The mean and median will increase. And the mode will not change. I don't expect the mode to change because I don't have any other 7-foot students. And if I did, then this would increase the frequency, sure. But I don't have any other 7-foot students that I measured. As far as range and standard deviation, the range is going to change. The range will increase because that was the largest student. That's the tallest student. The range will increase. And the standard deviation will increase. Everything's going to increase but the mode. Why will these things increase? Because it's a higher high. It's a larger spread. This pulls up your average. This pulls up your middle number. And this doesn't pull up your frequency. So as a whole, that's what I'm expecting. I'm not going to verify it by recalculating everything. We can confirm that, right? Number 38, thought-provoking. To find the P% trimmed mean, I don't remember what that means, but they're going to tell us. But to find the P% trimmed mean of a data set, first order the data and remove the lowest P% of the data values and the highest P% of the data values. I don't know what percent means. Then find the mean of the remaining data values. Find the 10% trimmed mean. Oh, P is the number that they give us. The lowest and highest percent of the values. Find the 10% trimmed mean for the data set in exercise 8. Compare the arithmetic mean and the trim mean. Arithmetic mean means averaging them together from the original. And the trim mean, why do you think it's useful to calculate the trim mean of a data set? Okay. So let's go to exercise 8, find out what that information was. I also might have to find them in my work because I did do the problem at the time. So I'm going to just copy and paste these numbers over here. Give me a moment. Bring in these numbers over here. I think we need to, there must be 10 numbers because they're talking about percentage, 10%, upper and lower. So I'm going to come up with what we did in number 8 at the time. And this is number 38 now. Oh, I had it typed at the time. This is beautiful. Okay. Let me just bring this stuff over then. Disregard what I copied before. Ignore. Okay, number 38. Here's number 8 info. Right there. Now, the best info I'm probably going to work off of is the ordered set right here. There are 10 numbers. We have to remove the lowest 10% and the highest 10% to find the 10% trimmed mean. So we have to remove from this set the 3 and the 18 because there are 10 numbers. 3 represents the lowest 10%. That's 1/10 of them. And this is the highest 10%, 1/10 of them. And we're going to look at this trimmed set right here and calculate its trimmed mean. So its trimmed mean, x bar trimmed, is going to be adding 8, 14, 22, 36, 50, 65, 80, 95, 111. And divide that by 8. 111 divided by 8 is 13.875. Exactly. I'm not going to round that one, but 13.875. The original mean was 13.2. So, did they say compare them? Yeah, compare them. So the trimmed mean is higher. The trimmed mean is higher. They said, why do you think it's useful to calculate the trimmed mean of a data set? This could remove outliers, potential outliers. 3, I was talking about this. 3 feels outlier-ish with that 8 there. Maybe, maybe not. But it takes out some things that might really throw the things off in a big way if they're massive extremes. Trimmed means, and it depends on how much you trim them, but we state that, right? This isn't the mean. This is, because I think we stated the median when I was looking, oh, right here. I didn't copy it over, but on part B, I think it said we chose the median because kind of the outlier skews. Trimmed means can remove potential outliers that skew the data. That skew the data. Did they say outliers is misspelled? I'd say that is a proper plural word. So that's what I'm going to say for that one. Now, it depends on how much you trim. Maybe you have to trim a whole bunch of it, but you have to also mention that you trim that data, right? By the way, this is the mean with this removed. It's good to remove both, though. It depends. All right, last question here is number 39. There are 3 parts on problem solving. How long have we gone? Ooh, we're going to probably pass 2.5 hours. The circle graph shows the distribution of the ages of 200 students in a college psychology 1 class. There is a 37-year-old, or at least 1% of them are 37. Majority of them are boom, boom, boom. Find the mean, median, and mode of the students' ages. Okay. The tricky bit, 200. I didn't see this. The tricky bit for this is, you got to figure out how many students there are of each of them, right? Now, 30%, these percentages, I'll tell you how many there are in each. 30% of 200, you got to do 0.3 times 200, but that's 60. 60 students here. 14% of 200 is 28. 20% of 200 is 40. 1% of 200 is 2. 35% of 200 is 70. You can confirm that these add to 200. 60 plus 70 is 130, plus 20 is 150, plus 28. Wait, did I do that right? I might have done something wrong. 60 plus 70 is 130, plus 20 is 150, plus 28 is 178, plus 2 is 180. I did something wrong. 20%, 40. I was adding 20. Let's do that again. 60 plus 70 is 130, plus 40 is 70, plus 20 is 198, plus 2 is 200. Got it. Okay, so that's the 200 students. So there are 20 19-year-olds. There are 70 18-year-olds, right? So when we do the mean, we got to add all 70 18-year-olds together. You're adding all their ages. This 18-year-old, this 18-year-old added together. Boom. And then there are 60 19-year-olds. There are 28 20-year-olds. There are 40 21-year-olds. And there are 2, not 1, there are 2 37-year-olds. We got to take that and divide by 200. I don't think the sum of the ages really matters, so I'm going to do this all in one fell swoop. So 18 times 70 plus 19 times 60 plus 20 times 28 plus 21 times 40. If you're curious about the sum, I'm not going to write it, but if you're curious about the sum, it's 3874. We divide that by 200, and we're getting 19.37. So for the mean, X bar equals 19.37 years old as an average. Even with the 37-year-olds, but, there are only 2 of them compared to all the 19-year-olds, so that kind of makes sense. Median. Now, the median, here's the thing on the median. I'm not going to write a whole list, right? But I did write these in order by age. There are 70 18-year-olds, there are 60 19-year-olds, etc. I can write 70 18s, 60 19s. There are 200 students, so the middle value, you would say is 100. It's actually 100 and 101. Those are the middle values. If there are 70 18-year-olds and then 60 19-year-olds, that adds to 130. The 19-year-olds is every person from person 71 to person 130. That means that includes person 100 and 101. The median is the average of 19 and 19, which is 19. So the median is 19 years old. The mode is the most frequent one. This is where mode is pretty relevant for what we do here. Just by kind of histogrammatically kind of seeing these as they are. More 18-year-olds than anything else. I'm not saying it's the most relevant measure of center. I'm just stating that it kind of stands out as relevant in what we do. Is that all we had to find? Yes. Identify the outliers. How do the outliers affect the mean, median, and mode? I'll tell you what, they're not going to affect them very much, if at all. They're not going to affect the median. They're not going to affect the mode. They'll barely affect the mean. I don't know how much. But the outlier is the 37. The 37-year-olds. 37-year-olds. There are two of them. Yeah, actually, I'm going to write them. 37 and 37. 37 and 37, clearly different. They probably stand out in the crowd. Heck, I'm 36. So how do the outliers affect the mean, median, mode? Let's try. I mean, normally I don't calculate them. But I want to calculate them here just to show you the difference. The median is still going to be 19. The mode will be the same. It'll still be 18. But if you remove them, what does this sum look like? Remember the sum was 3874? That's by adding. Now it's 3800, and I'll divide this by 198. I'll have less students. Now my new mean for this one, it will be smaller, but how much smaller? Take a guess. I don't know. The new mean, 19.19. What was it before? 19.37? Couple months difference on average now. No year substantial changes. Median and mode are same. Could have it changed the median? Yes. Could have it changed the mode? I'm not in this case because the most frequent one was still most frequent. Median isn't changed because the 19-year-olds are still the ones that fit in that realm. There are 198 students, and now the middle numbers are 99 and 100. The 19-year-olds still fill that area of those ones. So median and mode are the same. Last one, part C. Suppose all 200 students take the same Psychology 2 class exactly 1 year later. You're adding an age to everybody, right? Draw a new circle graph. Draw a new circle graph that shows the distribution of the ages of this class and find the mean, median, and mode of the students' ages. Well, the only thing that's going to change, I guess I can get rid of the quantities I have. The only thing that's going to change are their ages. Mean, median, and mode will change of the things. They'll all add a year. But on the graph, still the same percentages. Everyone just gets a year older. So these 18-year-olds are 19-year-olds. These 19-year-olds are 20-year-olds, etc. Now these guys are drinking. These guys are 38. Boom. So no change on that. How do mean, median, and mode change? By 1. You get to add 1 to the measures of center for these. So mean goes to 20.37. I don't have to recalculate anything. I'm just going to put that, not the year-old part. Median was 19. Now it's 20. Mode is 19. The majority of them are 19-year-olds. And there's that. Okay. All right, guys, that'll do it for this one. So this is Mr. Robinson. Thank you so much for watching, and thank you for indulging me in the slower lecture and kind of, telling some stories in between. If you caught some of them, I hope they were quite interesting to you. And hopefully this is a good start of, I want to see what's coming up next as far as all the sections. I'm going to read them out to you guys. We're going to look at box and whisker plots. So that's a lot of stuff regarding median-esque things. You're going to have medians in there. And ranges. Shapes of distributions. We'll see where they get into there. Two-way tables. Okay. You hit those in IM2 again. Choosing a data display. I don't know what that's going to look at just yet. Thank you guys so much. That'll do it for this one. This is Mr. Robinson. Take care, and I'm going to see you in the next one.